So where are we? So this morning, we started off with DC resistivity, talked a lot about charges, currents flowing through, things like that. Fundamentals of EM. I think maybe the thing that could get you to take home from that that's different than what is usually done. Usually, if you look into PEX, and this is certainly the way that I was taught or learned anything about electromagnetics, is that obviously you got Maxwell's equations, and you're going to work with them. And the first thing you do is you transform into the frequency domain. And the advantage of the frequency domain is that now you just have one frequency, you got one system of equations, nothing, the frequencies aren't coupled, you can solve them independently. And then you get out a solution. The disadvantage of the frequency domain is that there's a large number of things that are really not very intuitive because the currents that you have sort of are represented both as an in phase and a quadrature phase. So there's always like two things that you need to think about. And then that transfers to the data, right? Because now you've got a magnetic field, for instance. That's either in phase or it's out of phase. You've got all of these kind of real and imaginary parts. And if you try to look to see, okay, how are the currents flowing as a function of frequency in the system? You can look at absolute values of currents, but it's, if you try to parse it out into looking at a complex number, and you got the real and the imaginary, and they're trading off, and so it's just harder to track of things. I find that. Whereas if you go to the time domain, now things are actually really much more simple. So despite the fact that the solution of the equations is potentially more difficult in the time domain than in the frequency domain, the understanding is more simple. So we change this around. So when we're presenting this, we're presenting everything generally in terms of time domain first, so that you can watch the currents as a function of time and get the idea of what's happening. And then you can see that certain currents are being attenuated in this kind of a medium, or they're passing through in this kind of a medium. And then once you've got that, then now when you go to the frequency domain, it's like, okay, I got it, right? So the currents are going here, and the only thing is like they're sort of partitioning into an in phase and a quadrature phase, but nothing else is of importance is particularly happening. So by working in the time domain, building up your intuition of what's going on, and then going to the frequency domain, I think really, really simplifies things. The only place that we introduced frequency domain first was in this sort of simple example with the coils, because that's a natural place to work with frequency, and you can kind of see that, okay, if I've got a secondary current that's in here, it's a secondary current, but it's part of it's in phase or part of it's out of phase with the primary, and then you can build up that response function. But for virtually everything else that we'll do in this course, we're going to be looking at time first, establish what you get, and then frequency. And I hope that makes it easier for you. It certainly kind of did for us, and it wasn't really until the last year or two that we recognized that's probably a better way of introducing these things. I'm not sure how many people know Peter Annan. Is that a familiar name? Anyway, Peter Annan's a guru in electromagnetics. He develops, he's sensors and software guy, developed all of the GPR systems. And I was talking to him when we were trying to put this together, because we're also inviting people to participate in the development of Iam GeoSci. And I was talking to him about frequency and time, and he says, yeah, frequency domain is just so hard to really try to kind of explain your way through. And he said, I definitely much prefer time domain. So there at least you have it from a couple of people. kind of seem to benefit that way. So anyway, so we went through the fundamentals. So I hope you've got some idea for that. For frequency domain, the thing that comes up is skin depth. That's always there. And for time domain, it's diffusion distance, how far these fields actually decay in a conductive medium and in a particular time. We then looked a little bit at the systems, in particular the time domain systems, and then we've just done a case history with respect to water resources using a SkyTem time domain system. So the SkyTem is something that people are using a lot. The other common system is a VTEM survey. They're all, at some level, they're all the same. They've got some kind of a waveform, current goes on, and then current goes off. You measure during the off time, and you do switch polarities so that you can get rid of noise. There's a couple more case histories that are in the notes that I think we won't go through at this point. The first one was a mineral deposit in Canada. It uses what's called helisand data, so that's a gap geophysics. There's a large loop on the surface of the Earth, and the data are acquired by a magnetometer in the air, and then you could go ahead and invert that. So it's a ground-based system, but with a helicopter receiver. It's kind of interesting, and it's time domain, but the same principles apply. The other one was another mineral deposit in Spain. It's called Magdalena. There might be some opportunity to come back to that. The thing I like about that particular case history is that it's very well thought out. It uses a number of different types of time domain systems to try to see if you can't find the deposits, and it also uses some borehole EM. So it's possible we'll come back to that. And also, as people are kind of going through this, if there's certain things that come up, you say, wow, that's a really interesting case history, not only for me, but maybe for a few other people too, then it would make it worthwhile to do. And we might be able to squeeze it in today, or we could probably try to fit it in tomorrow. So we're pretty flexible. I mean, our goal is just to try to tell you something that's interesting and useful. We've got a lot of material, and just primarily kind of open doors here as best we can. So we've done an example in the frequency domain. So or in the time domain. So let's now work in the frequency domain. So as I said before, there's really not any fundamental difference between time and frequency. In time domain, you've got this kind of a pulse, and then you get data that look like this. In the frequency domain, you've got this kind of an input current, and your output signal looks like this. So those are the two essential things, but they're all based upon Maxwell's equations in the interim and inducing currents in here and then generating magnetic fields outside. So we can go ahead and do the same thing that we did before, but now with a frequency domain system. So here's a loop, again, vertical magnetic dipole, sitting 20 meters above the Earth's surface and half space of 100 ohm meters. So we're going to look at the current density. So again, the currents are going to be circular, but now they're going to be flowing all the time because the transmitter is flowing, except the currents are going to be going like this way, and then they're going to go that way, and then going to be that way. But at any particular time, they're circular. And if we look inside the Earth, right at the Earth's surface, the currents are kind of concentrated in there. So here I'm looking at the amplitude, so it's some currents are going in, some currents are going out. That's just the amplitude. And the B fields, again, because you've got circular currents, have maximum metering. B fields, they still exist out here. things. See, they're a bit complicated. Let's look at a high frequency. So at a high frequency, then the skin depth is really small. Okay. So we use this formula for skin depth. Skin depth is 16 meters. So the currents are kind of concentrated right near the surface. At a lower frequency, let's say 10 kilohertz, skin depth is 50 meters. So you can see where the currents are. And as you go progressively lower and lower frequency, these currents again decrease in amplitude, but broaden out and kind of diffuse through the earth. That's why we call this a diffusion process. It's not like waves where you've got pulses that are going through. This is just diffusing through. And if we look at what's kind of happening at 100 kilohertz here, things are really close to the surface. As you get lower, it comes down like that. And the magnetic fields can be complicated, but they're still observable up at the surface or where your receiver is. Now let's go for a layered Earth. So again, we've got the same kind of setup that we had before. We've got a uniform half space, and we've got a layer in there that could be either quite resistive or conductive. So we already now know kind of what to expect. If we just have a uniform Earth, then those are our currents. Have a resistor in there, then we're not really seeing very much. They're still kind of concentrated at the surface. If we have a conductor, okay, then we see both currents in the upper surface as well as in that conductor. And if we have it very conductive, virtually everything is concentrated in that very conductive layer. So again, this is the same kind of flavor that you have in the time domain. And then the B fields in each of those cases look like that. And as I said, we're measuring up here. Again, the thing that is perhaps most diagnostic are these sounding curves. So now in time domain, you just have one curve, right? But now in frequency domain, you've got two. One, you've got a real part, and the other, you've got an imaginary part in phase and quadrature. So that's what they look like for the half space. If you put a resistive layer in there, then you get the dashed lines. So a little bit of difference, but not really very much. Put 10 ohm meters in, and you start to see a very substantial difference between the half space and that one with the layer. And if you put a really conductive layer in, with sounding curves that will look like that. So again, exactly paralleling what we had for the time domain, except here now you always have two curves instead of one. So now let's go back to the shielding problem. Okay, so remember in DC resistivity, we put our current electrodes in like this. We have a resistive layer in here that affects things. For DC resistivity, remember we weren't able to push currents that go through this particular layer. Yes, this was the result that we had there. We put that layer in, and we got an enhanced apparent resistivity, and that was just all due to this one layer. With the inductive source, however, so if we put in an EM source and we have that sort of sitting right in here, here's our currents at a particular frequency, and what we see is that we have currents that are induced in that upper region in here, and here's our resistive layer. So there's nothing really that's happening, and our sphere underneath is illuminated. So that's perfect. So the resistive layer just doesn't hamper us. So if we, sorry, I got a little ahead of myself. So just to go back here. So this was the homogeneous Earth. That's what we get. If we now put the resistive layer in here, okay, then we've really got no difference between the currents on this sphere and the currents here, so that the sphere has not been affected by that resistive layer. Yeah, and if we just have the resistive layer itself, then we just end up with this. So we still get currents that are coming through. So the bottom line here is that, conductive source, we're okay with trying to see through a resistive layer. And if we look at our sounding curves here, without a sphere, you get the red and the black lines. But with the sphere, and either with that resistive layer or without that resistive layer, you get these quantities here. So they basically exactly match. So you're just completely. So what happens with a conductor? Well, in the resistivity, we saw that if we've got a conductive layer, the currents go in, they get channeled around, and they come back up. So they move, something like that. So you're really not seeing that conductive sphere. However, if you try that now with the EM, and now what would you expect with the EM signature? Mark?
Well, the charges will be, you see the currents in the conductive layer. So
yeah, so you're going to end up with, essentially the same thing as you're going to for the DC resistivity. So if you have the conductive layer up in here, then that conductive layer is going to shield the sphere. So here we have just the sphere. Here we have a conductive layer with the sphere. Now you can see if I put the conductive layer in, I've got a lot of currents that are just sort of sitting right there, and I really don't see that sphere at all. So the bottom line is you're still moved. I mean, if you've got EM and you put in a conductive layer, you're still not going to see anything that's below, but as a resistive layer, you can see. So that's really kind of the take-home message here with respect to EM. EM is always connected with trying to find conductors. If that conductor happens to be something you don't want, like a layer, that's it. You're still going to see it. You may not see through. So the case history that's associated with that is one for groundwater. It happens in Australia. So this is an area called Buprano. How many people know about this particular case history or what has gone on? All of the CSIRO people. So here's the setup. We're down here in the Murray River, and we've got agricultural region up here, so it's all in green, hatched, and brown. And there's a lot of irrigation that goes on in here. So you've got irrigation that are coming down. There's a floodplain in here called the Murray River floodplain. And you got river water that is going along here. And the concern is really the salts and the contaminants from the irrigation that come down here and affect what's happening on the floodplain. So we've got an elevation map that looks like this. So this is a high elevation, and this is all low on a floodplain. And like the real question is, okay, what's going to happen to the area around here at the base of the irrigation, as well as around the floodplain, and what's going to happen to the water that's actually in the river. So if you've got a lot of contaminants that are coming in, they can flow into the river and then be transported down. So that's a problem. So there's a lot of over irrigation that has happened here. There's a lot of saline water that gets kind of into the floodplain as well as into the river. And the question is, okay, can you determine where this stuff is, how it's being transported to mitigate things? So floodplain salinization is like a major issue, and the ecological damage that is happening. Just as an example, here's sort of a picture of what has happened, all the salt that has come in, really salinated things, and completely kind of devastated the vegetation there. So that's an issue. It's been around for quite a few years, and this mission was taken up by CSIRO and I don't know what other groups to see what they could do for monitoring this, and to see if they could find some way of mitigating the negative consequences here. So one of the things that they were experimenting with was the following. So suppose that we've got stuff that's coming in at this point. So it's coming off of the irrigation region, and we've got salts that are coming in. They're coming into the river. Suppose you could take some wells out here, okay, and pump the saline water out, and they pump the saline water out, put them into evaporation ponds up here, but to reduce the hydraulic head here and actually perhaps get saline water to move up this way and increase the amount of fresh water that is there. So if we pull a lot of water out here, then we might get fresh water that's coming in here and restore the vegetation. So that was sort of the basic idea. And here was one of the salt interception wells that was commissioned. So that's 2006. So that's more than a decade ago, as far as what they're doing. So they had 3 of them. They're pulling salt water out. The little test area that they had, there was a strip in here, a few hundred meters long, and they did a survey over it to record what the electrical conductivity was as a function of depth. And this was in January of 2006. And the blue is resistive, so that's like fresh water. The red is conductive, so that's saline water. They pump for a year, I think it was, and then they go back and they repeat the sampling, and they find that you've got this kind of distribution. So now it's blue farther inland, so that means that by pumping the saline water out, they've actually kind of freshened the area around here, and made kind of substantial difference. That's 50 meters there. So that was part of their experiment. But in addition to that, what they wanted to do was to collect some geophysical data and see what information they could get out about this area, both at a particular time and also perhaps from a time-lapse view, see what was happening. So, yeah. So the properties then that are really of interest are electrical conductivity. So we've got the fresh water being resistive. So maybe like 100 ohm meters or 0.01 Siemens per meter. And then the saline water being 1 ohm meter, a couple of Siemens per meter. So that's actually quite conductive. And as I said, here was the transect that they were looking at. So that's where they made measurements and electrical conductivity values. So now they're going to do a survey that goes over the entire area. And they're going to use a resolve system. So this is a frequency domain system. So this was flown in 2008. So here's their transmitter, here's the receivers. And the resolve system has got a number of these solids, it's covered, and then it's got a number of coplanar coils. Each of them works at a different frequency and each separated by a different distance. So we've got frequencies all the way from sort of like 400 to 130,000 hertz as for the coplanar and also coaxial. So the green lines are the lines at which the resolved data have been collected, and the goal is to collect those data, interpret them, and see what we could get for conductivity structure. So this is the result of that, and I think this is kind of an interesting plot for a number of reasons. One is that, at least for some of the people here, I think if I had shown this plot first thing this morning, there've been a lot of questions about what is really going on. But I think now we can actually take a look at this plot and see, okay, how much have I actually learned in 3 hours, and what sort of things make sense or not so much sense. So first of all, I'm just going to tell you what each of these are. So this is 380 hertz. There's the in phase. There's the quadrature phase. This is a higher frequency, same thing. This is the sounding curve, and this is a response curve. So what sort of information can we glean from that, and what are these pictures telling us, and how can we put it all together? So what we have plotted on here is that ratio of the secondary to the primary field. And when we were working with the 3-coil system, we ended up with this as a response curve that kind of told us how things got partitioned between the real and the imaginary part. So first of all, let's just think about these two pictures here. Okay, so we've got a top line and this line. So first of all, which of those lines correspond to something that is the shallowest structure? Yeah, so the high frequency, remember the skin depth is dependent on frequency. So this is a high frequency, so it's got a shallow skin depth. So this curve here, these values are telling us more about what happens at the shallow depths. And this is, with this one, we're looking deeper. Secondly, there's an in phase and a quadrature phase. Right? So I think for a lot of people this morning, might not have known what that was, but now you realize that, oh, all that's happening is that my signal is kind of getting partitioned into two parts, one that's in phase with my primary, one that's out of phase, and they're both carrying some information about what's there. Okay, so the next part is that this is a sounding curve. So this is frequency, and that's your response. It actually looks like this. So my question is, this sounding curve, is that telling us that we're over a region of really high conductivity or low conductivity, and how do you kind of come up with that conclusion?
Low conductivity.
Low conductivity? Yeah. And what brings you to that conclusion?
to respond so is for primary response not too much quadrature.
Right, so here's our response curve. And we actually see more in phase, right, than quadrature, right? So if we look at the solid curve here, that's high compared to here. So as we come up here in frequency, we're going up. So it's like this part of the curve is kind of on here, and this part of the curve, the quadrature part, is coming down. So that sounding here is really quite consistent with this curve and this being actually a high induction number, which means high conductivity. Low resistivity, high conductivity, which I think is probably what you meant. So that's good. So we've got a number of things about a picture that I think a few hours ago would have been perhaps a little bit mystifying to some people, but kind of a bit of a calibration, like, okay, maybe I'm not wasting all my time here, I'm actually learning something. So we've got these guys here and our response curve. Yeah.
Maybe I'm missing something here, but if I look at the 380 hertz maps, left and right in phase quadrature, the amplitudes of those signals look roughly the same based on just a sort of qualitative look at the colors. So I would have said you're closer to, on the response curve, sort of the induction number of about 1, or something like that. Have I got that wrong? What makes you say that the in phase is larger than the quadrature? Or are you talking about the sounding curve?
Well, I'm actually talking about the whole sounding curve. Notice at the lower frequencies, there's less difference here, right? At the higher frequencies, there's a big difference. So if we look at the high frequencies here, you can see this is a lot more red, okay?
Sorry, I was just looking at the top.
Yeah. So I think these things are actually kind of consistent with this, and probably something about this area is not so unreasonable for that for the lower frequency. So we're going to take these data and we're going to invert them and a three-dimensional image. So again, these inversions are done in just 1D and then stitched together. We've actually done these as full 3D inversions or as stitched 1D. In this particular area, there's places that the 3D and the 1D differ a little bit more, but in a lot of cases, from a general perspective, the 1D in this case actually provides some reasonable interpretation. So the conductivity model, which is stitched, is 3D, and here's a slice of it through at a depth of 8.6 meters. The color bar here, this is highly conductive, so that you can, this region is in here, and these regions in here are resistant. So blue is always resistant. And as far as fit to the data, we do a good job of fitting, observed, and predicted. So our interpretation from that is the following. We've got sort of conductive material that is sort of sweeping into this region here, which is not unexpected given the hydraulic head. You've got high topography over here, and so stuff is kind of flowing in downhill, and we see that we've got high contamination of conductivity in here, and interesting that in regions out here, there's kind of blue towards this end, which is indicating that there's perhaps fresh water that's going out this way. Just a sec. It's a bit better. Okay, so that's our interpretation from the conductivity that these parts of the stream are actually gaining salts parts, and these parts here are actually losing that fresh water up to the side. So they're flooding the region with fresh water. So our synthesis is that here's our hydrogeologic model. We've got irrigation up top here, stuff is flowing down. Here's the Murray River, and yeah, we can make some areas where the salt is coming in, and also where fresh water might be going up. Yeah, so actually this is kind of an interesting example. It has continued. There were data that were collected in 2006 and 2008. There was both frequency domain and time domain data, and both of those have been inverted and give almost similar results, but there's little bits of difference which might be indicative of time-lapse variations of what's going on. And then in 2015, these data, the SkyTemp data, were run again, and flown, and they have been inverted, and they show a much more significant time lapse. We don't have access to those data, but from the point of view of monitoring what's happening and with airborne data, this Bupranow example is actually pretty nice. Anybody here into drones? For what respect? For geophysics, or just for playing, or for monitoring your neighbors?
No, I've been experimenting with them, mostly theoretically for things like BLF ideas, and also for chemicals.
Well, we were in Tokyo not so long ago, and interacting with people there, and it was just kind of interesting, because one of the major projects for AIST, which is their kind of one of their national labs, they were developing a system, frequency domain Iam, for drones. And if you're going to do something, you have to sell it, right? You need to get people to buy in on these things. And the question is, where's the application? What are people going to resonate with? And this one in Tokyo is kind of interesting. So as a whole, there's quite a few places that AIST is interested in from the point of view of using electromagnetic geophysics. You've got soil and groundwater contamination, EM modeling, and data acquisition in the sea, both for hydrocarbons and also for seafloor massive sulfides and gas hydrates. That's also big there. Radioactive waste disposals, acid mine drainage, and geothermal power and mineral deposits. So this was from their brochure, and I took one look at that and I said, well, EM can play a huge role in all of these things. Their particular case that they were interested in, there was an earthquake and then a slide that had come down. So we've got a landslide that comes down, and it buried a couple of cars and killed a few people, right? And so using that as an opportunity to say, okay, well, if we actually had an airborne system that could have flown really close to the ground, we could perhaps have figured out where these buried cars were, and that would give us an indication that at least there might be a car there, and maybe somebody's trapped in there or not. We don't know, but that was sort of the context by which they formulated all of this. So you've got a system that kind of looks like the Resolve system, but they wanted to make it miniaturized and have it on a drone. So that offers some technological challenges. First of all, the drone itself has got a lot of electromagnetic noise, And so you need to have a sensor that's quite a ways away. So here's the drone, and then here is the transmitter and receiver. So it's just like the resolve system that we just talked about. And this has to be far enough away from the drone that you're not getting a lot of EM signal from that. So what this plot shows is the signal level that you get by just sort of hanging this thing a certain number of meters from. So 3 meters, you get a signal that looks like that, 4 meters like this, 5 meters like that. So you actually have to be 5 meters away from the drone before you get noise levels that are sufficiently small. So that was the first thing. So and then they're trying to fly this as close as possible to the ground. And here's, again, where some of the basic principles that we've just looked at are important, because you've just got a little coil in here, so that gives you a magnetic dipole, and that falls off as 1/r cubed. And then we have any currents that are generated in here. They kind of look like magnetic dipole fields, and they're going to fall off as 1/r cubed going up. So the result was that because of that geometric attenuation, you actually had to be pretty close, and you could, something that was 1.5 meters deep, you could detect. Something that was 3 meters deep might be a little bit more iffy. So they went to the area, data. These were the survey lines that were collected, so not exactly straight, but they've got data. And then what was plotted up here was the in-phase part. So remember, so in-phase, quadrature phase, if you're looking for a conductive target, then you want to be up on that upper part of the response curve. So it's going to be, your signal is going to be primarily in the in-phase component. And what you see is that there's a large anomaly here that turned out to be, you can read Japanese, that's the shallow car. And there's a hint of an anomaly here, which was the location of the deeper car. But again, I think this is interesting because it's just all the same stuff, but just kind of repackaged in, it's either a bigger system or a smaller system, but you're still looking at something that's effectively a dipole transmitter and contending with geometric decays and signal to noise. Okay, so that takes us through time and frequency systems. So we should ask you a question to make sure you're awake. Just a second. Okay. So we have these days aren't purely inductive. They actually involve putting a current into the ground, connecting two ends of that wire, so that it looks like it's kind of a galvanic transmitter, but it's just they're going to put in a time domain signature for a waveform. And the question is, what is that actually going to happen? So these are going to be grounded sources. So we're going to look at the backgrounds of these, look at conductive targets, resistive targets, kind of talk about how a grounded system works in a whole space. I've got a couple of case histories. One has to do with a Deccan track. So it's like the use of this for a larger scale kind of project. And then maybe one for DC resistivity type of survey. We also have a tutorial on marine EM, which I'm interested if they've been involved in that, because there was a lot of confusion in the early days of marine EM about this thing called the airwave. How many people have heard of the airwave? You raised your hand for everything.
I was just lucky enough to attend one of Stephen's seminars, Steve Cousins.
Oh, okay.
On that subject.
Yeah. And then there's methane hydrates, which I understand might be of more interest in Brisbane than here, but I'm not sure. How many people are interested in methane hydrates here? Okay. Well, that made that easy. Yeah, so it's always difficult to know like what kinds of things motivate people. All right. What's our examples? Well, there is the marine. Marine is actually very fruitful from the point of view of different applications of problems. So there's hydrocarbons. This has been the big thing for de-risking of very expensive wells. But there's also gas hydrates or methane hydrates, seafloor massive sulfides. These things are pretty prominent in certain countries, especially with Japan, and realizing like, okay, we could actually mine minerals just on the ocean floor. So marinium, various oil and gas enhanced oil recovery, methane hydrates, volcanoes, number of aspects of looking for minerals, and even our classic example that we've done before, taking the kind of the DC resistivity, but extending it, instead of having a DC source, put on something else that's got a time varying source. So the good thing about taking the material as we've done up to this point is that we've actually focused on two end members. The DC resistivity, which is involved in putting a current into the ground, and then remember we got all these charges that were built up, and we used those to get the electric fields. So that was our survey there. And we also did an inductive source. So now we've got a different part of physics that's going on. We get currents that are in here, but those currents don't generate. There's no charges on the boundaries, at least if this is very very resistant. So it's a different physics that has generated that. But if we look at this system here, where we've got a current electrode and another current electrode, and we've got a time-variant current through here that has got current's got some time variation, then we're actually going to get time-varying magnetic fields that are associated from that, and they're going to generate currents in here. So if we put them together, we still get currents that are kind of flowing through the Earth, kind of in a galvanic fashion, but we also get induced currents that are coming. So to try to kind of parse those out is really interesting, and it gives rise to a whole new set of surveys that you can effectively use. So we want to go through the basics of this and then look at some applications. So let's first of all look at an electric dipole in a hole space. So now we just got, so you can imagine just a little generator and a kind of short piece of wire. And so here's our currents that are going like this. So it kind of looks like a dipole. Electric fields fall off as 1 over r cubed, and currents follow the same. Just only difference is the factor of sigma in the conductivity. So now let's think about what's happening in a time domain experiment. So we've got a current that's going in, it shuts off, and then it stays at 0. Shut off. Our diffusion distance is given by this formula here. So at 10 to the minus 4 milliseconds, so this is really early, so at 0.1 microseconds. Here's what our currents are like. So they're like this. And our diffusion distance is only 4 meters. If we go a little bit later, at 10 to the minus 3 milliseconds, what's happened to the currents? So the currents now are starting to reduce in amplitude. This amplitude is much less than that. So we're still trying to plot things on reasonable color scales, but the amplitudes are decreasing. But you notice also that the amplitudes are decreasing. So it's like you have initially start off with sort of a concentration of current, and then gradually it's diffusing outward. It's getting bigger, and the amplitude is getting smaller. At a later time, diffusion distance is out at 40 meters, and things are really continue to diffuse, and they continue to do that. So again, this is a really good way to kind of think about what's happening in the Earth. If you can initiate a little bit of current in there, as you can with the dipole, and then you turn it off, and then you say, okay, well, what's going to happen to the currents? Well, they're just going to diffuse outward, so the amplitude continues to decrease, and everything just kind of eventually disappears. So in the frequency domain, what's going to happen? Well, we've tried to convince you that there's really not much difference between time and frequency. So with a time domain system, we've got a harmonic transmitter, so it's always on. There's always a primary field. And the data, they just get partitioned into real and imaginary part. So if we look at that kind of relationship, so this on the left side, we've got time domain, which we've seen. On the right side, we've got frequency domain. And a good way of kind of transforming between the two of them, I mean, it's not exact, it's okay, is if you're thinking about a time domain, something that's happening in the time domain, let's say at 10 to the minus 4 milliseconds, then that's kind of the same as if you had a frequency domain experiment at 1 over this. So that would be 10 to the 4 kilohertz. So if you look at 10 to the 4 kilohertz and you look at the secondary currents, they kind of look like this. At a lower frequency, you can see they're starting to get reduced amplitude and spread out. And lower frequency that, lower frequency that, and that. Okay, so nothing magic or different. You look to see what's happening at different frequencies, and that's kind of similar to what happens at, in the time domain that's reciprocal of that frequency. So early times, high frequencies. They're going to be the same. So they're going to look like that. Diffusion distance is that. Skin depth is given by that. Late times, low frequencies, they're going to look like that. So if you build your intuition in time, and you can use that then to kind of get a good idea of what's actually going to happen in the frequency domain, and then there's just this additional complication of taking your signal and putting it into a complex form. Okay, so here is now the really interesting question. So suppose I got this. I've got a current, okay? So my A electrode is going to be here, and my B electrode is going to be here. So I've got a wire. And it could be a straight wire like that, or it just could be a crooked wire. Sometimes it's called a horseshoe, and it's used a lot in mineral exploration. So now what I'm going to do is I'm going to put a time-varying current through this wire, and I would like to know what is going to happen inside here. Where's the currents? How are they going to vary if I put in any kind of a conductor or a resistor? And how do I kind of understand what sort of signals I'm going to expect? So we could put this ground source on the surface, and its ability to detect a target is going to depend on some usual culprits, right? What's the geometry of the target, conductivity? What's the geometry of the transmitter? What's the size? Is it going to be frequency or time? Which fields am I going to measure? EB, dBdt, and the location of the transmitter to the receiver. So there's, again, just a zillion amount of variables and lots to explore. But we just want to use a simple example to kind of illustrate the context. And then if you do that, then I think you'll have a good idea of what's going on. Okay, so let's start with this. So we've got a grounded system. And the first thing that we're going to do is we're going to put a constant current in, and we're going to turn it off at some time t is equal to 0, and we're going to leave it on. So at steady state, we already know what's going to happen. That was the very first thing that we did this morning. So steady state, we're DC resistivity. Right? So I've got current that goes in here. You see it flows back here. My currents inside the Earth are like that. Okay, so what's going to happen? What's going to happen when we turn the system off?
We're going to create a magnetic field in the wire.
Yeah, so there is a magnetic field that's coming from the wire, right? So your comment was again?
When we shut down, we're going to create a magnetic field through the wire. When we change the electrical field.
Close, not quite what I would say. Anybody? Pardon me? What? Going to go the other way. Current. So the current's initially in the wire. Okay. So the current's going this way, right? And then if we, so and this current initially has a magnetic field. So that's right. So it's got magnetic field, right-hand rule, right? So there's circulating currents around here. Okay. Now I'm going to turn it off, and then you're saying what? The currents flow
All the way around.
so the currents are going to flow this way in the wire?
The ground just shuts down and you have a change in flux.
Pardon me? Yeah.
The current in the wire goes to 0, and you
Right.
have the dBdt.
Right.
Flux. And then you induce current in the ground by the dBdt. It's conductive.
Okay, good. Anybody else? Yes?
It's going to decay down like smoke rings. Dissipate.
Okay, so a lot of those things are right. So let's just take a piece by piece, and let's break it into, first of all, two things, like the wire, okay, as well as what happens to the DC. So first of all, you were saying that there, kind of get a current, a reverse current. So the way that the Earth likes to respond is that the moment that you turn the current off in the wire, then there's a magnetic, there was a magnetic field that was coming from the wire. Okay. There's going to be a response of the Earth to try to keep that magnetic field the same. Right? So what that is doing, it effectively is going to transfer the current that was in the wire. Okay, it effectively transfers that to the Earth. So there's now an induced current in the Earth that's traveling along that same path. Right? So that means that you now have a current that's in the Earth. And now once we've got that, now we can think about well, what did we have from the dipole and hole space, right? Remember, it just kind of decayed and lost amplitude and decayed. So here is now what we expect. So immediately after we shut the current off in the wire, there's effectively an image current that is now at the surface. And as far as, that means that at this point here, the magnetic field hasn't changed. It used to have the magnetic field, from the wire, but immediately after that, there's still a current up there. It hasn't felt any change. But as a function of time, this current that was there now kind of diffuses down and outwards. And yeah, if it had been a circular route, then it would have kind of looked like a smoke ring. Now it's kind of like a smoke wire or something. It's just a current filament that is gradually moving down and just diffusing away. Okay, so that's perfect. So that's the wire. Okay, what about these other currents that were here? So initially we had a steady state that was those currents. What's going to happen to those guys?
As the charges go back to sort of the uniform charge density, there's the opposite current towards sort of the opposite current density to what they separated in the first place. Like if you look at the secondary potential charge, you have a distribution of charges that is not in equilibrium. So once you turn off the current, they somehow go back to.
Right, but in here, if it's a homogeneous half space, there's no charges that are there. They're just currents.
Yeah.
Once you've got a current that's ever in the Earth, and you now no longer have any kind of forcing function to try to generate, kind of keep it there. And it's just like, okay, we're out of here. We're just diffusing. We could diffuse away and go to zero. So expect for the ground currents. So these currents that were here, they're all set up. The moment that you take that forcing function off, then it's like, okay, I've got whatever distribution of currents I've got, and then they're just all going to dissipate. So these guys will now move outwards and downwards and gradually lose their amplitude. So that's the two effects, and there's actually two very different effects that are going on here, right? One's from the galvanic part. Turn that off, you get that set of currents. The other is an induced current that's coming in because you've changed the magnetic flux, and that current density is now free to move outwards. So our end solution needs to consider both of those guys. Let's look at some numerical examples that'll help things. So we're going to do a grounded source in a half space. So we've got an A current here, so it goes back there. So those are our initial currents. This is on the horizontal plane. But this is the vertical plane. I think maybe we'll just concentrate on here. If I look at the numerical simulations for this half space, so here's our AB electrode. So here's our transmitter. The moment or shortly after I turn things off, you can see where the current density is. So here's the currents up here. A little bit later, you can see how those are sort of moving down a bit later, like that. So that is exactly this current that I've got, just letting it kind of expand outward and downward. Okay, is that? Turn the current off, get an image current that's developed. Nothing to keep that going. It just kind of decays. Now it becomes a little bit more interesting. That was interesting enough, but this becomes good. Suppose I had a target. Okay, so now just a cube, and maybe I should have done that. Okay, rats. Here's my line. Okay, and I got this target here. Okay, so initially I have a a current that's kind of going from here through the target. Okay, so I've got the DC resistivity, and now I turn it off. And what are the things that are going to be affected in this target? How is the target going to react the moment that I turn this current off? I mean, let's even think about the Earth being quite resistive. Right? So now if I've got a line of current that looks like that, so I've got a magnetic field that looks like that, then what's going to happen inside this target body? Quite, yes. What happens to the magnetic flux? Right, okay, so all these things are fitting together. The moment that I turn this primary field off, okay, there's now a changing magnetic field here, right? So that changing magnetic field, is going to cause, an EMF in here, that's going to give rise to currents, and we can even get the direction, exactly, get the direction of these currents by recognizing that those currents need to flow opposes the change. So here's the scoop. So I'm going to get vortex currents that go here. So here's my magnetic field. It's coming in like this, right? So now I'm turning that off, and now I'm going to get currents that are in here, and I know which direction those currents have to be because they have to oppose the change. Okay, that's all the minus sign. So that means that those currents have to be going in that clockwise direction. So I'm going to get vortex currents that are in there. In addition to that, I'm going to have, I still have galvanic currents that were flowing through here from what I had before. And also I've got here that are coming from that shutoff. Those are actually going to diffuse downward, and they're actually going to look like a galvanic source as I come through. So now I'm going to have currents that are flowing this way, okay, because of this image current that's going down, and that's going to cause some currents. So there's a couple of things that are one time. One is thinking in terms of vortex, and the other is in terms of galvanic. So let's just here and see if we can't sort all that out. So we got this grounded wire, and so we go from A to B. And you can tell here, well, you tell me, is this a conductor in here or a resistor? It's a conductor, yeah. So see how things are kind of snaking in, it's sucking the currents in. So that's a conductor. Okay, so it's going through that way. This is the steady state at just before shutoff. Look what happens at a very early stage after I shut off. So I now get flux on this prism in here, and that sets up circular currents in here. So the flux was coming in, the currents are coming like that to oppose, and most of the currents are still actually concentrated towards the top because that's still the closest that I have to my transmitter. A little bit later, we can see how these currents are into the conductor. So they're still circular. So these are vortex currents. And a little bit later, so the amplitudes are going down here. So yellow is not the same intensity. So a little bit later, the currents are flowing like this. And yeah, so there's still vortex currents here. Now what's interesting is that as for the next time here, look to see what's happening. And we've got currents. So these are the current lines are traveling this way. So these are no longer circular inside the body. These are galvanic currents that are coming about because, you know, as the current in the earth is diffusing down, you know, it's still a current that looks like that. And, you know, eventually it reaches the prism. In this case, a bulk of the current is actually coming through as galvanic current. So this is kind of what we see with if we have the system with a conductor. Initially, we have just galvanic currents. Early times, we'll get vortex currents, and at late times, we'll get both vortex and some portion of galvanic currents that are coming in. So that's the mechanism whereby we could illuminate a buried conductor in a background. Okay, any questions? So two components, and it really helps to think about, okay, what's happening with the initial state galvanic stuff, and then what's happening with the wire time variable.
Does that mean that the field in between 1 and 10 milliseconds, the field produced by that secondary magnetic field would rotate?
Sorry?
So I'm looking at the vortex current, so that would produce a field in a ring. Sorry, a ring around the current like that.
Mm-hmm.
But then the field produced at 10 milliseconds, the galvanic current would be rotated.
Yeah.
So the magnetic field would rotate.
Yeah, exactly.
Yeah.
Exactly. So which makes it all kind of a little bit complicated at some point, right? Because there's just a lot of stuff happening. But that actually is what's happening, and the two you kind of have an idea of the two sort of fundamental things that are going on. So now it is a question of, okay, so given that you have something like this, you're in charge of your exploration budget, and you have these potentially like, okay, I think this would be good from the point of view of illuminating the target, so I'm exciting the target. Which field should I measure? I'm going to go out and measure some data. So if I have something that looks like this, for electric field, I could measure EX, EY. Can't really measure EZ. Go ahead and ask. EX, EY, EZ. You've got 5 fields. Which ones would you use? So all the MT people, you go out and collect 5 components. EX, EY, HX, HY. Okay, so suppose you didn't have enough sensors to collect all the data. Which ones would you collect?
XY.
Pardon me?
XY.
X, but E or H?
H.
H?
X and HY. EX, EXY. If we don't have enough coils.
Okay.
Yeah. If we have 2 magnetic coils.
Yeah.
Then we will collect HX, HY. For E, we collect EX dipole and the EY.
Okay. Yeah. That's kind of collecting on the basis of you only have a certain number of sensors. But let's see if we can do one step better. If you had to prioritize Okay, so let's suppose you've got two electric field sensors. You could do EX, EY. Okay. In this particular case, which one would have more signal? Which one would be a better choice? So somebody over here said, well, who said?
EX.
EX. Why?
Voltage current would be strong.
Yeah, so you've got EX. Okay, so if you look here at how the currents are flowing, okay, they're flowing like this. So there's a lot of current in the X direction. In fact, there's no electric field in the perpendicular in the Y direction. So EX, that looks like good. That's what you'd collect for the DC anyway. So and here this is pretty good. So and look now, think about the vortex currents that go in here. So vortex currents are like this. And so at the top, which way are the electric fields going? Well, they're like this. They're in the X direction. So that's cool. That's a good idea. Let's take EX. EY is not going to be very sensitive. It's going to be basically 0 along here, well, because of all the symmetries and the way the fields are. So the point is here, if you can, not that because you never know what the exact object is that you're looking for, but in a case like this, you could make that judicious decision of like, okay, I'd like to get EX. Okay, so that's the EX. How about magnetic field? Do any bother? Yeah. So look at this magnetic field that's coming out here, okay, from a wire. That's out of the page. So that's an HY. An H component in this direction would be good. So an EX, an HY. Anything else? Vertical, yeah. So HZ might be pretty good. Okay, let's see. So here's EX. Here's our object here. Here's our half space. And here's what we have with the conductor. So at 0.04 milliseconds, it looks like this. So it's a little bit different than half space. But stuff really hasn't had time to kind of diffuse down. At later 1 millisecond, look at this signature compared to this. So it's hugely different. So EX is really diagnostic, and even at 10 milliseconds, it's really diagnostic. So EX would be a really good component to invert, and you'll have lots of information about that volume. Similarly, BY, as we've already discussed, has got a lot of information. So we look, especially at 1 millisecond here, and 10 milliseconds, it's very distinctive compared to the half space. And BZ, yeah, it doesn't tell you very much right along that line of symmetry, but notice you've got all of these distortions because the secondary fields are, magnetic fields are kind of going up on one side of the wire and down on the other side of the wire. And so that's distinguished in here and gives you a signature of the bottom. So there you go. I mean, that's actually quite a bit, right? You kind of now understand, okay, how are the currents being developed as a function of time? Where are they going? What's their direction? Which fields am I going to measure? And in this case, yeah, an EX, HY, HZ. What happens if you put a resistor? Anybody? Yeah.
There's no induction of the galvanic current, so don't move around it.
Perfect. You must work for marriages. So. Yeah, so if, remember we've kind of been through this, that, you know, if you've got a resistor, then there's no EM inductive response there, right? There might be electric fields, but there's no current. So let's see if that kind of works out. So here's a resistor. And yeah, so you can tell now it's kind of being pushed out around the resistor. If we turn it off, and at 0.04 milliseconds in that XZ plane, you see it looking something like that. So you got the currents that are coming from that image current. They're coming down like this. And yeah, there's our resistor. Later, there's a resistor. So there's nothing, there's no circular vortex currents in here. It's just currents that are going this way. They gradually, everything kind of diffuses down. This guy stays blank, nothing happening. And that continues and everything just dies down. So all that we have, and James is 100% right, the only thing we have are galvanic currents, right? So we started off with steady state, and then later on, these guys diffuse through, right? But there's still currents that are going in this direction. They're just diffusing through. They encounter from the resistive body. They flow around it. And there is charges that are built up on that, okay? But there's no vortex currents, it's just galvanic. So which field now? Yeah, EX, still going to be good. Good to go. So EX, yep, 1 millisecond, kind of looks like that. So there's definitely information in there. What do you think about the magnetic fields? Not much. You know, there's currents in there, but the magnitude of magnetic fields are pretty small. And yeah, there's hardly any difference. So in the end, yeah, looking for resistors, electric fields are pretty good. Which is why, of course, for anybody that's connected with the hydrocarbon industry and you think about C4AM for hydrocarbons, you know, the method of choice was let's take a grounded dipole, electric dipole, and just tow it through the water. There I've got an electric field source, and I'm going to measure electric fields behind there. That's your first order information. There is information from you know, the other components, but it's not nearly as good. So data summary. So if we have a conductor, EX, BY, BZ, that's useful. Here's the half space. So here's your conductor, half space with the resistor. EX is useful in all of these, and for conductor also the B fields. Now what happens if you didn't make things more complex? So now we take a conductor or a resistive block. Let's take a conductor plate. And now we've got to kind of worry about coupling issues, right? So we've got to get kind of current that's going into this guy. And you know, there are certain geometries that you can kind of intrinsically think, well, that's good coupling, that's bad coupling. This is really good coupling, right? Because we've got magnetic fields that are coming from the wire, they're going to be inputting on there. So, you know, the total flux through that surface is going to be pretty big. So you'd expect some pretty big currents, vortex currents that are coming in here. This is not going to be a very good coupling for the EM part, right? Because there's really very little surface area for the magnetic fields to get. So that's going to be pretty hard to detect. So you can see that things like when you've got complex geometry, you know, you really need to excite in a number of different directions. And really, invariably, as a rule of thumb, you at least want to do two. You want to do two orthogonal polarizations for illumination. more if you can, but you can see if you had changed the orientation of the transmitters this way, you picked up this much better. And that's really about as far as we can go. I mean, I think you can see that if we just had a grounded wire source and a block, it's already a lot of stuff to kind of carry through and see, okay, where do I have my vortex currents and how are all the currents behaving? And at some point, like, okay, I kind of get the basic principles, but if I want to know details, I just got to do forward simulations. So that's where the forward modeling comes in and allows you to just try various scenarios, see what you get, and then use that for your basis of survey design. I think we should probably break for, what time is coffee or what time?
We're ready for 2:30, so when you're ready, we're ready for coffee.
Oh, maybe I'll just do this one. No, let's do coffee. Let's share coffee. Oh, okay. So, yeah, so I don't know what to do here. I think maybe we should just we have
we can ask online, or I can ask. I can go
Why don't we ask Suzanne to see if she can get one? That would be great. Oh, sorry. This is right after. Okay. Oh, okay. Yeah. Oh yeah.
She's just left for now. Do you have to do a space station? We can put on USB because I just don't use the same password, that's all. So we put a USB stick and we'll get access to the computer to that.
Right.
So I'll go grab a case and reach around it.
Well,
Yes. In terms of like what I so really diving into the way that I would typically approach my job is simulating. If you've got a relatively simple model, I mean, like target, right? but I mean, floor simulation is a powerful way to do that. And so we're looking at parametric models and doing sensitivity analysis. And that can be really interesting. You actually get a handle on how sensitive parameters are. And that is
Yeah, that's.
so
I think that's one thing we'll see in terms of,
yeah, yeah, absolutely. Well, that's really it's simple for showing a sphere below the layer.
Yeah.
Like that actually starts getting towards
the brain,
realistic.
it gives the
Yeah,
brain,
it does. It does.
a lot of times, like, it's one that you miss out on this. That's all I can say. Hey,
Yeah.
It's one big area I think. Like, the contract is
Yeah. So I've done a lot of comments. And so that's
so all the examples is that
quite a number of them. So most of them, like with yeah, also with the forward simulation examples. And so yeah, that's actually like my forward simulation. I mean, it doesn't like large scale to large. That's more. No, it's not. Yeah, can I see it?
and it's normally wasn't probably not like stuff that was
Yeah.
that's what always because always models they're not don't capture. So I was always wondering if there's a better way.
And so what would you typically do? I mean, because often, you know, we do for if you know more about the system, like you can absolutely mathematically quite you don't know anything.
I don't know, I think it's an interesting thing to do with. I was wondering if you guys, let's say,
Yeah.
GA and some work.
Yeah, no, noise is one of those things that everybody says.
It's important. Yeah, it's just.
But yeah, like, yeah, so I've done stuff on sensitivity analysis, but not, I mean, that's actually something that we have machinery in place to actually build it out of the impact. So that's not something that but like, in terms of software, I know exactly where and go through and look at sensitivity with respect to your noise model. And like take derivatives on those. That would be an interesting thing.
Especially about able
Yeah. Sure, yeah.
Receiving
Yep, yep.
always moving around and rotating.
Yeah, and you're not exactly.
So you've got issues and
So that's actually something that we could do. A lot of the pieces are around in order to actually simulate your sensitivity.
Yes, that's true. Yeah.
So that those sources could actually.
So they one thing that they also already. So he was continuing to see, which is good, but it's good for sensitivity. But from a sampling noise point,
Yeah, but we go through and actually like compute derivatives on all those things, which does give you a very tangible and if I change my angle as well.
We always just want to when we would use it, how use it.
Yeah.
How does that?
Yep. Yep.
So like,
Yeah. Yeah, no, that's a good point. That would there's yeah, so 6 is now yeah, search for in terms of, well, he's got like a couple of comments.
It's okay, yeah.
Yeah, he's always got something else on the go. So, yeah, he's big into machine learning these days.
Yeah, just go.
Yeah, there's it's interesting to also see because the size of the world all of a sudden is like thinking about there's stuff that we learned in inverse problems that they just like haven't figured out yet in the machine learning world. And so there's a lot of like that space. There's a lot of room. Like I think at some point there's going to be a really interesting sort of knowledge transfer.
Yeah. One that's the goal is a lot of this. Fortunately, the processing costs.
Yeah.
And it's good news. So I think
And you're on that. Okay. Yeah.
Yeah, some contract work on the
Yeah. There's a little bit that we're sort of getting started. A lot of that stuff, I think it's interesting, and sort of packages that everybody uses, but right now they are black boxes.
Yeah, they're pretty simple.
Yeah.
And it changes
So there's some stuff that yeah. So we're actually like playing around with getting some stuff. It's so useful to be able to just get all of the nonsense. Like,
yeah, well, even with this stuff,
yeah.
Exactly.
Yeah.
A bit of background, sort of getting
Yeah, exactly.
That's amazing.
Yeah. Other than that, you're right. Insurance zero. Yeah. Simpeg is, and we haven't. Yes. Yeah, so all the sequels are working. There's MATLAB for Apple. The Simpeg is so there's a whole different style. Yeah, so they're sort of I mean, there's like a lot of the knowledge that is embedded in things. It's like translated to something. But yeah. Yeah, and much more digitally in it. Like it's very smart. Yeah.
And is it slow?
So we don't have like massively parallel and all of that yet. We don't put that in mind. It's not there yet. I mean, the solve is consistent. We still be interfacing the same solvers. But still, like, there's a few things that are quite different to figure that out again. If you want to do that modeling, yeah, well, and we've got like mailing lists and all this sort of stuff. I can give you my email, and you're most welcome to ping me and get you sort of like where the conversation Oh yeah. Yeah, I mean, if that's actually dive into, I will, and I can show you some weird and scary. Yeah. We got feedback forms on all the tables.
Perfect.
And then a couple people were concerned that we wouldn't get to IP. So
Okay, we'll get
it.
We'll make sure we get it.
Yeah. Sounds good.
Okay, can I ask everybody to sit down? So did you want to?
We can do it now, or I can do it like at the end.
Okay. So we've got a number of case histories. It's just going to be too long to go through all of them. But I think the good news is you've got examples. I mean, you've got the slides. And so if there's particular things in there, there is tomorrow. We have an opportunity to bring something up, especially if there's more than one person that's interested. There's been a couple of people that have been concerned, like, oh, we might not get through to the IP today. So I'm going to make sure we do that. So we'll kind of not do so many tutorials and case histories, but at least kind of get through the major part so that we do natural sources and IP, and then maybe talk just a bit about the future. So we got a couple of hours, and I think that's probably go. And then Lindsay's also going to talk a little bit about some of the apps and how you find them, and then you might want to download one or two tonight and play around, and then we can come and pick things up again tomorrow if that works. So maybe I'll just do one very quick case history on the use of scale grounded sources. This was actually that comes from India when we were there. This is a fellow by the name of Kurt Strack. And in India, they were really interested in where the sediments were beneath the flood basalts, the Deccan basalts. And for people who have kind of interested in long-term evolution of the Earth, those flood basalts in the Deccan troughs kind of occurred about the same time as the asteroid that killed the dinosaurs. And there's lots of kind of talk back and forth about who was the major culprit and how did those two things interact, because there's millions of cubic kilometers of basalts that flooded out of there and very much caused environmental change for the Earth. This was motivated by hydrocarbons, or discovery of hydrocarbons. So the setup is, here's India, here's a region of interest, and there's these flood basalts, and they're interested to know if there's sedimentary material underneath the flood basalts. There was initially a DC resistivity line that went across here, and that was interpreted to give it a section that looked like that. So there were sediments that were found, but were about how thick they were and where, and there was a lot of questions about what's really there. They decided to do what's called a low TEM survey. It's a long offset time domain EM. And it's a grounded transmitter. And then you collect, so you put a transmitter, and the transmitter lines were, I don't know, sort of a kilometer long. And then you measure electric and the magnetic fields along here. So mostly EX, EY, and HZ were the bullets, but they could actually measure all components. To try to kind of look at survey design and see could we detect something, the base model was basalt material at top, maybe 150 ohm meters, sediments that were 20 ohm meters, and basement about 1,000, and then just vary the thickness of the sediments to see if you could see something. What we're looking at here is time, so it's a time domain survey, so you're measuring stuff at individual time channels. And for each time channel, you could convert it to an apparent resistivity. There's actually two formulas for doing that, one that's valid at very early times, one that's valid at late times. But the result is you can still apply these formulas and see how much change you're getting as you're varying the thickness of the sediments from 1 to 3 kilometers. And you can see that, okay, we've got some signal there. And then you could also vary the resistivity of the sediments to be anything from 20 to 100. And again, you're affecting the data. So it's kind of a crude survey design, but it shows you, okay, I changed the model, I've got some sensitivity to that, and maybe then the experiment will be okay. The data were collected, stacked. This is kind of stacked apparent resistivities. The thing about this is that it just kind of shows you that there's not a lot of noise in the data except for certain time channels that are effectively later. The processing in this case was pretty simplistic. This was a few years ago. Basically 1D parametric inversions. And there's a couple of interesting lines. So there's one across here. This is line R. As you go across here, the inversions gave an upper region here for the basalts, sediments that were actually quite thick at 16 ohm meters, and then a big resistive base below. As you go down to G, that sedimentary thickness decreases, And as you go to K, it's pretty much gone. I think the interesting thing about this is that prior to this low temp experiment being done, they had kind of had it reversed. People had thought that the sedimentary thickness actually increased towards the south. So that was major outcome of this particular experiment. And yeah, there's a few kind of details. One is on a particular line profile, ended up with getting an image that looks like this. So here is that sedimentary package. It kind of peters out here, and the resistive region underneath sort of comes up. And it was initially a question of, what was that? They went out and they looked, and they said, oh, there's a dike up here. Turns out to be a resistive dike. And it was just kind of a confirmation that, okay, the geophysics is actually looking like it's working. We got something that's resistive. We go out, we actually find a resistive dike. So everybody thought a little bit better about that. And the thing about conductivity is that it's not necessarily the value of the conductivity which is the ultimate influence, but it's really the conductivity thickness product of things. So there's kind of an equivalence that occurs. And tomorrow, for those who are attending, we'll do the magnetotellurics, and you can see that you can get different models that have different conductivities and thicknesses, but if the products are the same, more or less gives the same response. So the conductances were obtained here, and there was a region of high conductance for the sedimentary region up here. They decided to go ahead and drill a well there, and the result was that from the time domain EM, they kind of predicted this as the thickness of the basalts, that as the sediments, and then basalts underneath. And when they went and they subsequently drilled the well, it actually came out, really actually quite nicely as far as finding that transition between the basalt and the sediments, and then also to the basalt. So I think the point about this, and the reason I chose it, it's kind of like a bigger experiment. We're looking at something that's scale. It's a time domain EM. You're recording electric and magnetic fields, and you're inverting them and getting something as far as the large scale structure for what's there. And that was extremely valuable. How many people are kind of involved in data that are contaminated with EM coupling? Okay. There's a lot of really interesting stuff that we've been doing, other people have been doing, that are looking at trying to get the maximum amount of information out of your EM signal. In some cases, for instance, in DC resistivity, I'm just going to kind of outline the problem, but we're not going to go through it. So, because you're actually now in good shape to do this. So when we talked about DC resistivity this morning, we talked about turning the current on, right? And then the voltages stay up at some value, and we use those voltages and then invert them to get electrical conductivity. Good to go. We turn it off, and then we've got no input signal. The IP is going to be generated in this region in here. We'll talk about that. But the point I want to make here is that, okay, I'm turning this guy off. So the moment I turn that current off, what do I got? I got a time-varying magnetic field that's going everywhere. That's going to be inducing currents. I might actually be able to get some signal from that. So when you look at the responses that are from this, there's actually an inductive response that comes in here. That we can show. I'll show you that tomorrow. we can actually use that to invert and recover for the electrical conductivity. In general, what is done these days is that information is thrown away, and then you just use the late time stuff for your IP signal. So what this case history was going to do, it'll take you through the steps of actually using data that is traditionally thrown away and showing like, wait a minute, that stuff is actually really valuable. If I can record that, I can get some very useful information. So that has to do with DC and Iam. Okay. So what I'd like to do now, okay, here's our plan. Because there's quite a few people that are interested in magnetic tellurics, right? Yes. So we won't go into depth. But I'll give you an overview. Yeah, we won't do GPR, and then we'll do IP, and probably try to get up by 5. So what I want to talk about now is natural source EM methods, in particular magnetic tellurics, and do an MT case history. That's actually going to be on geothermal energy. And as we've traveled around the world, that has been something that really resonated with a lot of different countries. There's also something called Z-axis tipper or Z-temp. I think it's not so important here in Australia because of your massive cover, but in lots of places it is. I probably won't talk about that. We could talk about tomorrow if people are interested. So what's our motivation? Why do something else? Well, it's basically scale. So we've got volcanoes, right, that we'd like to find the structure of, or in hydrocarbons, the base of the salt, geothermal energy, trying to find out what's deep, groundwater issues, mineral targets, and tectonic settings. And I realize now after coffee that the one thing I should have put in here is a picture of Australia with your thick regolith, right? Because it sounds like there's a lot of people that are trying to figure out how the heck to get through this, and MT is one way that could possibly do that. So what's required to see deeper? Well, again, we can kind of go back to the basic, if we have a control source, and let's suppose that we've got a loop, and we've got a magnetic moment, okay, that's our strength, but we've got a signal that decays as 1 over r cubed as we're going down here. And now we get currents in here, and they also decay as 1 over r cubed going up. Okay? So if we look at the total geometric attenuation, that's 1 over r to the 6th. That's a really big number. It decays hugely quick. Okay? So how could we overcome that? Well, we can't do anything about the currents coming up to the receiver. They're always going to go off as 1 over cubed. But maybe we could do something about the transmitter. If we could make a transmitter that was really big, so if we could make like a really, really large loop transmitter, then we basically have a vertical magnetic field coming down. So we could have a plane wave that's moving down. And in those conditions, there's no geometric decay from the transmitter. There's only a 1 over r cubed. This is the reason that people are kind of keen on having a large scale transmitter. Of course, it's pretty difficult to build 1,000 kilometer by 1,000 kilometer transmitter, but fortunately, Mother Nature gives us a hand. So we've got not scale. So here's the sun, and here's the Earth. It'd be kind of amazing if it was a scale. Here's our magnetosphere that's sitting out here. We've got the solar wind that blows this guy back. So close up, as we come into the Earth, you can see how it kind of looks like a dipole. As you go out farther, things really get distorted. We can get solar storms on here, and that gives rise to particles that come in and gives the aurora borealis or the aurora australis. Australis. How many people have seen that? Anybody? Do you have to go to Antarctica? Okay.
If you go to Tasmania, it's another country.
Okay. Anyway, yeah, it gives rise to, well, southern lights, I guess you'd call them, sort of shimmering spectacles of light that are actually quite miraculous if you get a chance to see them. And then there's lightning strokes that happen, all give sources, electromagnetic sources. So here's a short movie to tell you what's happening. So that's a solar flare. Now stuff's coming out. Lots of charged particles. There's our Earth's magnetic field. Comes around. It merges with the field lines at the back end. And there's something called a field line reconnection. That brings the particles back in, and then they funnel along the magnetic field lines into the north and south pole. And as these particles come in, they interact with various oxygen, nitrogen atoms in the ionosphere, and the particles then cause those to be excited, and as they relax back down, they give off a photon. So you see different colors of light depending upon which atoms are being excited and what their energy states are. I would just play that once more. It's kind of a cool movie. Yeah, so these solar flares also cause potential damage for hydroelectric or for electrical grid systems because you got time varying fields. Yeah, so that's a complicated process. This whole business of field line reconnection is challenging. Then once that happens, those particles are brought back in and then they get funneled. So particles, as they're moving, will just spiral along the field lines in a radius that's ever decreasing until they get down close. So that was the solar wind and that kind of activities. The other things that can happen are lightning strikes. So we get a lightning stroke here, and so that's a current, right? So now it gives a magnetic field that propagates out. The Earth, as we've seen, is very conductive, right? I mean, even if you think, 10,000 ohm meters, that's still a lot more conductive than the atmosphere at, 10 to the 8th ohm meters. So this is a highly conductive unit. The ionosphere, at about 110 kilometers up, is highly conducting. So what that means is you get electromagnetic energy. It's got two basic high reflectivitors, one above, one below, and we kind of have a waveguide. So that permits energy to travel basically all around the world. And so if you're sitting up in, if you're down in Australia, I mean, you could have tropical storms far north of you and you still feel that energy. The power of the natural ambient field looks something like this. So this is periods, that's eight orders of magnitude in period. This is sort of the power of the magnetic field. Kind of goes up like that. There's a little bit of a notch in here at an interesting part, about a tenth to 10 seconds. Yeah, but we can still get data. So now the question is, okay, so now imagine you're on the surface of the Earth and you've got this plane wave that is coming in at some angle. The question is, okay, well, what happens? Well, it's a wave, and so it follows Snell's law, and that means it's going to get reflected and refracted. So some part will be transmitted, and some part will be reflected. Here's our wave number. We actually saw that earlier. So that's the wave number. It's a complex number. If we're in a quasi-static regime, as we've been talking about for most of the day, things reduce down to something like this, so that the transmitted angle here is related to the incident angle via this ratio. And because the electrical conductivity is so big, basically that means that irrespective of what angle this stuff comes in at, it almost refracts almost vertically down. So even waves that are coming in at 89 degrees, hit the Earth and they go sort of basically straight down. So you can think, this is why in magnetic tellurics, people often think about the primary signal as just being a vertically propagating plane wave, and that generally works pretty nicely. So now we can revisit some of the things that we did earlier. We had talked about skin depth, and so now we've got plane waves that are coming in. So if we've got high frequencies that come in, then their skin depth is very small. Lower frequencies see deeper. The bottom line is, any of these EM waves as they're diffusing through, you only see really a portion of a wavelength. So somebody was asking about seismic and EM. I mean, the equations are kind of the same, but the relative weights of the dispersion and propagation terms are very different. So we only see, a wavelength or something. So control source versus natural source. We talked a lot about natural sources, what we have in natural source. So we can lay out a loop, measure EX or E and H fields. In natural sources, the receivers are the same, both E's and H's, but the sources are distributed. They're random in space and they're random in time. You got a lightning strike there, later you got one over here, right? So things are very random, and that causes a fundamental difference here. We can't invert these exactly the same way. So we have to handle this business of randomness. And the way we do that is introduce a ratio of fields. In Maxwell's equations, if I change the source, both E and H behave in the same manner. So if I somehow took a ratio of them, then that effectiveness or the effect of the unknown source would kind of cancel out. And that's basically the idea. The way of formalizing that is to introduce what's called a transfer function. So now the electric field is equal to this quantity Z. It's called the impedance tensor. It's a 2x2 tensor, and times H. So this is H, that's just HX, HY, so horizontal, and E is EX, EY. And here is your transfer function equation. So the goal is to obtain these impedance estimates, and then with that you could think about going ahead and inverting the data. Before we do that, it's kind of interesting to bit more how all this behaves in a uniform Earth, and also identify two modes that are important. So if you imagine a plane wave coming in, then the plane wave could come in so that the electric field is into and out of the board and the magnetic field is perpendicular. So it's traveling this way. So the propagation is E cross H. So you've got E and an H, and then it's propagating this way, right? So in this particular mode here, the electric field is parallel to the Earth's surface, and that's called the TE mode, transverse electric. So the electric field is kind of parallel to the structure. The other mode is the TM mode, transverse magnetic. In that case, the magnetic field is parallel, and the electric field will be perpendicular. Those are actually two very important different kinds of waves, and they interact very differently with the Earth. For half space, it doesn't matter, of course. The impedance is just EX upon HY. And then, just like we did in DC resistivity, there's an analytic solution that the resistivity is related to the impedance structure by this. So we can measure EX, measure HY, take the ratio, square it, compute this relationship here, and get the apparent resistivity. And there's also another datum called which is the phase, because Z is a complex number, and that phase for a uniform Earth is pi by 4, 45 degrees. So in 1D, our general equation is like this, but for 1D, the impedance tensor has just got off-diagonal elements, and they're actually equal to the same value. So things become very simple. So suppose that we have a layered Earth, 100 ohm meters, 10 ohm meters, and 500 ohm meters. Then the apparent resistivity, which depends upon the frequency that you're working with, can be evaluated as this manner. And if we did this for high frequency, so now we're going from high frequency to low. The reason we do that, high frequencies have small skin depths, so you're somehow looking close to the surface. So this would be near surface. So you can see what the apparent resistivity is here. So that's 100. So we're just seeing this guy here. As you decrease the frequency, then you're looking deeper, and now you're starting to be affected by this layer here. So it's going down. It doesn't make it down to 10, but it kind of gets down. And then as you go even deeper, then it goes up and it rises above 100, up towards 500. So the apparent resistivity curve is kind of doing what you'd kind of hope or suspect, and phase does something else. So that's 1D. There's an app for this, and allows you to, put in different resistivity structures and see what you get for your impedances and apparent resistivities to phases. In 2D, things change, and you now, again, based upon the stuff that we've done already in the course, you're starting to get a pretty good idea about, like, okay, what could possibly be happening here. So let's first look at the 2D case for the TE mode, where the electric field is parallel. In 2D, the diagonal elements are 0, but the off-diagonal elements are no longer the same. So for the TE mode, we're going to look at EY upon HX. So EY, so let's suppose we've got a transition from 100 ohm meters to 10 ohm meters, right? So we'd like to find that out. And we're going to do a transect along this direction here. And we're going to look at the electric field in this direction and the magnetic field in this direction. So when we do that, the electric field in this direction is uniform. So it's just constant. And the magnetic field goes from something that looks like this to this. And the apparent resistivity, when you put all that together, starts way over here, 100 ohm meters. It's good. And comes down here to 10 ohm meters. So the apparent resistivity is kind of doing sort of kind of nice thing. It's kind of what you think about. So suppose that I change things a little bit and I said, oh, let me look at the TM mode. So in the TM mode, now this electric field is going to be pointing in this direction, and the magnetic field is going to be that. If I did that, what's that going to do? I mean, could we, first of all, kind of get a sense of like, okay, the electric field, what's going to happen there? A gold star or a free cookie? Anybody answers that? Both DOT guys. So now, okay, so let's suppose I've got an electric field that's pointing in this direction. So I've got currents that are going to try to go there. What's going to happen to the electric field? Right. So the has to be continuous, right? So the current is going to go through there. But the conductivities are different. Same thing that we had for the fundamentals of DC resistivity. There's got to be a change in the electric field. And the only way we can change that is to have a charge on there. Different kind of behavior. And if we look to see what happens, the electric field on this side looks like this. And then immediately as we cross over, it goes chunk. Yeah. So the apparent resistivity now looks like this. So way over here, it's at 100. Down here, it's at 10. In between, it's kind of all mucked up. So that's the difference between a TE and a TM mode, and it's why it's so important to kind of have some understanding about what's going on, and you can relate that to discontinuous changes in electric field, charges, and stuff like that. In 3D, it's like everything else; it just gets complicated. There's no special symmetries, there's no special conditions. It's just complicated. So you can't really wend your way out of things. One of the important things in this in magnetic tellurics is let's think about what we're measuring. So we're measuring EX and HY, or E's and H's. But we're measuring those as a function of time, right? We're just putting up a receiver and just recording things as a function of time. So electric field, this is 1 second. The function of time looks something like this, right? And the magnetic field also looks something like that. But when we were working with our equations, we were looking at EX over HY in the frequency domain. Right, so we're measuring stuff in the time domain, but we're actually needing stuff in the frequency domain. Now, if all of these were just from a single fixed source, it really wouldn't be a problem. We could take the Fourier transform of this, and the Fourier transform of that, and take a ratio, and we might be good to go. That's not what happens, because we've got a whole bunch of sources all competing at the same time. So I have a stochastic process here for my signals. So I've got to somehow deal with that. And I'm going to have to deal with that by taking some averages, some ensembles of data averages, and try to get an estimate of what the average impedance values are. The other thing that's required is generally a remote reference station, because we've got lots of local noise, and we need to somehow contend with that. So usually they'll have a remote reference. For the processing the MT data, and this is something I think maybe we can talk about tomorrow a little bit, because the community around the world that we talk to are really interested in this problem. And at one level, everybody's saying, "Oh, well, we know how to do that. There's this kind of code, Edwards code. There's this code or that code, right?" But then you say, "Well, if you wanted to change something, you had something different, would you know what to do?" And then they say, "I have no idea. This stuff is all a black box. It's really complicated." So we'd like to change that. We'd like to get a group together to work on processing of various kinds of signals, but in particular MT, so that everybody can contribute and also kind of open up some boxes here so that you can understand what actually is going on. Because knowing what the data are is extremely important. Anyway, the kind of general idea is you take a time series that looks like this, divide it up into a whole bunch of little segments. We'll do the Fourier transform of each of these little segments, and then generate impedances where you're kind of doing successive averages of products of these guys with magnetic fields from the remote. So there's some stuff in there, but that's kind of how you do it. You need the remotes, you need to have multiple representations, and do lots of Fourier transforms and averages. Inverting the data is pretty much the same as we have when we have controlled source. For an MT problem, the length, the size of your grid has to be, a couple of skin depths away. So again, skin depth plays an important role. Perhaps the major challenge is you don't really know what the boundary conditions are in this case, because you could actually have, currents being funneled, up through the lithosphere and, contorting your signal. But that's just something to contend with. But otherwise, inversion of MT data is really the same as any kind of control source. So maybe, actually, does anybody have a question?
Doug?
Yeah.
Yeah, maybe I've got one. Could you work around the randomness of the natural sources by using the difference? So not looking at, for example, the x component of the E field, but looking at the dEx, having two potentials.
Or
Yes, and looking at the difference.
I have two stations. Well, anytime, I'm not sure how that, we have to think that through. I mean, anytime you're looking, it's kind of like,
Looking at the gradient of the E and H field.
yeah.
It's okay.
Yeah, I mean, anytime you're doing a subtraction of something, might give you something that takes care of some aspect of the transmitter. They do that in some borehole stuff when you're doing the rim data, right? Sometimes they do a difference, but I think mostly it's generally ratio. That'd be worthwhile. I want to do case history for Iceland. As for geothermal, is there any geothermal in Australia?
Yes, but
Yeah.
hot dry rock, Cooper Basin projects on that, but it's really far from the market.
Okay. This one's particularly nice, I think, because I think it's kind of at a little bit the leading edge of what could be done with MT, and also was done by one of my students who works with the Geologic Survey of Iceland. I think it's a really nice result, so we'll kind of flip through it. Yeah. So basically, Iceland, it's on the Mid-Atlantic Ridge, so it's being pulled apart, and these big dark spots here are sort of high temperature areas. So there's lots of fumaroles, lots of hot springs. Anybody gone to Iceland? Oh. Go to the Blue Lagoon? There we go. It's on my bucket list. So we've got these regions through here, especially that are very high temperatures, and there's a number of geothermal plants that are there, and Iceland gets a fair bit of its power at this point from geothermal energy. Here's the kind of geologic model for this. So suppose you've got a hot rock source that's here. Now you've got water that's kind of circulating through from groundwater, funneling in from elsewhere, interacts with this, and then it kind of convects in here, And there's a region up top that goes through a phase alteration, and this kind of turns to clay. So the bottom kind of resistivity profiles, you got near surface, more resistive rocks, maybe greater than 100 meters. And then you've got this conductive coat in here, this conductive smectite clay. Generally, this is the thing that is being sought. They want to find the bottom of this clay layer, and then use that as a potential for there might be hot water reserves underneath. So that's kind of what's being done. But you can take this one step farther. Water is actually circulating through here. This was fairly resistive, 250, 1,000 meters. If there's a lot of water that's circulating through, this might have a little bit lower resistivity than this core. And then you've got high conductivity structure beneath. So here's the sort of overall idea of what you might think might be there. And the goal is not only to look at the bottom of this clay, but also to try to find this guy. Okay. So here's the survey. It's a Phoenix system. It's got coils for measuring magnetic fields and little electrodes for measuring the electric fields. Survey, there was like 133 stations, frequencies. It covers many bandwidths, right? So 300 hertz to 0.001 hertz. So you're getting down to low frequencies so you can see. There's a remote station about 40 kilometers away, and the data are processed with Phoenix processing. There's 133 stations, but we're just going to look at a couple. So station 1 up here has an apparent resistivity that looks like this. So what we see here is a couple of things. First of all, at the surface, as close to the surface. So this is high frequency here. So this is at the surface. Both modes are together. So it's kind of like, it's sort of 1D and maybe a couple hundred ohm meters. And that stays for a while until you get much lower frequencies. And then they split apart. So then you get two curves. And you can see, okay, we're going resistive. There's something conductive. We go more resistive, more conductive, resistive. So you can imagine that, okay, at some scale, there's maybe 4 layers there to give rise to that. So that's this guy up here. If you go down to this point, then at location 3 here, we notice a couple of things. First of all, the overall resistivity has decreased by order of magnitude. And secondly, the two curves are different right from the get-go. But they still have a lot of that same structure. So we want to take those and now invert them. So now we're doing a 3D inversion of magnetic telluric data with many decades of frequency. The resultant 3D cube looks like this. So blue is material that's resistive, red is conductive. And this is kind of an interesting presentation. It's kind of like a section cut out of the cube. And then this is an isosurface of resistive material. So this is that resistive core that is of interest. And if we just looked at a section through here, then we've got this conductive layer up here, and then sort of resistors down here, and another conductor there. So how do we put all that together? The idea is that this is the clay cap. This region in here is that kind of resistive core, but this region here and this region here are less resistive. So these could well be the reservoirs that's connected with what we're looking So the interpretation is that this reservoir is actually corresponding to this, and the rest of the blues here correspond to that. And actually that comes out pretty well in the final synthesis because there's a number of boreholes that were drilled. The production wells and the hot. So what we're looking at here, this is temperature on here. So the purple, the magentas, those indicate temperatures. That's 350 degrees Celsius. So we've got high temperatures that are going in here. Here's one that is going into here, and it becomes very cool with respect to that. And over here also, we've got high temperatures that are associated with this region in here. And this region in here, which has a couple of wells, I mean, it's resistive, it goes in and it has some degree of high temperature, but there's just no fluids that are flowing through there. So it all kind of makes a bit of a consistent story, and the important thing is that we find the two reservoirs here and here, which are actually production reservoirs. So that was it for MT. The thing about Australia is it sounds like MT is actually a pretty important survey here, especially when you got big areas and you also have all this conductive overburden, and you need something to see through it. If it's 300 or 400 meters thick or something, and it's 10 ohm meters, you got to go down to low frequencies and have lots of power. Okay, so maybe what we'll do is do the DC, or we'll do the IP. Go. Oh. Is that better? Oh, dear me, I didn't notice that spot. No wonder I'm getting hoarse. Okay. That's why everybody's falling asleep. Okay, here we go. So let's do IP. What's motivation? Actually comes from a number of places. So first of all, there was that minerals prospect that we had this morning. We did NIM, and we did DC resistivity, and there were some useful things that came off, but it wasn't really diagnostic for the mineralization. There's permafrost that we're interested in, groundwater problems, massive sulfides, and geotechnical problems. And all of these are kind of bound up with the fact that the electrical conductivity actually is frequency dependent. So if we measure the electrical conductivity in the lab, generally you have a block of material, you put a voltage across it at a certain frequency, and you measure the current, and then that ratio gives you the resistance. If you change the frequency, you get a different number. So electrical conductivity or resistivity actually depends upon the frequency. And so it's regarded as being complex. So at really low frequencies, the resistivity might be really high. At really high frequencies, it could be much lower. And so it's got, again, a real and imaginary part of in phase and quadrature. And again, hopefully that makes sense to you, right? Because if you imagine that you've got a block, it's got here, and I'm putting a current, connecting it to the circuit, and I'm putting a current through it, and I got a generator, right? And that generator is putting out a particular sinusoid. And now I'm measuring the current that's going through this block. You find that some part of it is actually in phase and some part is out of phase, exactly the same as we talked about this morning. So what we're seeing here is that there's kind of an in-phase component and there's an out-of-phase component that happens. So this curve, the fact that the electrical conductivity or resistivity actually depends on frequency, might be extremely useful. And it's all bound up with talking about something called chargeability. So I'm going to talk about sources of IP, and perhaps for people who haven't seen it, having a conceptual model is really good. Just helps ground things a bit. And we're going to talk about IP data, some sections, and I'll show you an example. So first of all, the IP phenomenon, the fact that electrical conductivity is frequency dependent, is actually pretty complicated. I mean, if you really, really want to know exactly what's going on, everything is happening at a microscopic level, really surface to area issues, whatever kind of clay particles you've got down here. There's just all kinds of effects. These are microscopic effects, but they kind of combine and have a macroscopic manifestation. And the idea is as follows. If something is not chargeable, if we have a source that is like this, so we turn the current on, leave it on, turn it off, leave it off, and then reverse the polarity. If we looked at the electric potential that's measured, it would mimic exactly that. Okay, so it would look almost identical. Now, if the material is chargeable, I do the same thing, then what happens is the moment I turn it on, then it rises, but then there's kind of a continual increase in that voltage. It's kind of like an over voltage. And in fact, if you look back in the 1950s when this was discovered, that's kind of what people refer to. They talked about over voltage. And then if I turn it off, it does this kind of thing. So it's that manifestation that's really important to us, and that codifies what we call chargeability. So here's the conceptual idea about how you can think about chargeability. And I find it really very useful because it makes everything kind of fall into place. So suppose we've got a little, we're now talking at a pore throat level. So we're now talking, microns here, and we've got a fluid that's sitting out here. So the rock has got a little fluid pathway between one pore to the next pore, and initially everything is electrically neutral. So what's going to happen to this guy here if I now apply an electric field to it? So let's suppose I apply an electric field like this. So what's going to happen? Okay, the easy way to think about this is how could I apply an electric field in a particular direction? Well, if I want to apply an electric field in this direction, I could put a big positive charge here, a negative charge there, right? Good, so that's good enough. So now I think about here, I've got a big positive charge and a big negative charge here. Like charges, what? Repel or attract? Whoops. Yeah, so like charges repel. So if I'm sitting, if I'm sitting here, so the positive charges want to go this way, negative charges want to go that way. But if the pore throat is fairly small, especially the positive cations, they can't get through. So they just kind of clump up, right? And they'll continue to clump up, but you can't, put them put an infinite number there because if you get too many positive charges, now that actually reverses the field. So now a positive charge coming in here would feel like, oh, I'm getting repulsed by these guys. So there's kind of like an equilibrium that's established. So initially, everybody's going to rush that way, and then eventually it's going to kind of asymptote it out so that there's some end state. But then if you counted up the number of charges here, you'd see like, oh, there's kind of a big positive charge here and a net charge here. That's an electric dipole. That's why it's called electric polarization. And induced means just that, somebody's forcing it to do that. So this is a nice model because you can kind of imagine, well, I'll come back to it in a second. First of all, we have to tell you what materials are chargeable. So there's minerals, a lot. There's pyrite, chalcopyrite, graphite. These guys are all chargeable. And these numbers are in terms of milliseconds. I'll explain that later. But yeah, for now, just to kind of get an idea that some of these are chargeable. And also earth materials are chargeable. The main thing for chargeability is sulfides. And that's why the mining industry is so keen on IP methods, because they're very, very chargeable. Yeah, so there's a whole range of these. And as I said, all these are in terms of milliseconds. Okay, so why is that this kind of cartoon model very useful? It's useful because it really helps us understand what's going on. So we turn the current on like this, and the moment that we turn it on, we get this initial rise in the voltage. Now we leave it on, and now these guys start to build up. Initially, they start to build up quite quickly, right? So the voltage increases, and then eventually they just asymptote up to some end value, and you can't put it in. You've reached steady state. So that's good. And now we're going to turn this off, and the moment that we turn it off, we drop down by the same amount that this was. But now you got all these charges there. What are they going to do? Well, they're going to relax back. But it's all fluid. You got the charges there. It's going to take them time to get back. So there's a time scale that is required and to decay. The IP data, the net effect of the chargeability, and the term chargeability was, I think it was first introduced by Siegel, if not at least for the intrinsic chargeability being a parameter between 0 and 1 was introduced by Siegel. And effectively what chargeability does is to reduce the electrical conductivity or increase the resistivity. So that's why a material that's chargeable will have an NDC value that's up here. So it's a higher resistivity than it would be if it wasn't chargeable. So the effect of chargeability is kind of reduce what the conductivity was. And the theoretical value of chargeability is actually the ratio of this current here, this potential, the secondary potential, to the total potential, what's often called the primary. So if we look at this equation, that is really what we'd like to measure. It'd be great if we could go out into the field and measure that, but we simply can't, because that's happening at the same time we're turning on. And the other reason that we couldn't measure that is why? Exactly, thank you. Yeah, so right here, it's time you're turning off, all kinds of things are happening, right? You've got all kinds of induced currents, and so there'd be extra voltages that are there. So we're not going to be able to see something there. Nevertheless, we are going to be able to start recording, and we could maybe see that curve. And any manifestation of that curve is going to be related to chargeability. So here's what we do. So we look at this IP decay, and we could have as an IP data just the value of this at a particular time. So now it would be in millivolts or microvolts. We could also look at take 2 times and do the area under this decay curve. That's valid. So with IP, in this, the only thing you want is just grab something that's characteristic of what's going on here. Could be a value at a point, could be an integral, doesn't matter. Just define what you want to use and say, okay, that's something that's indicating chargeability. You can also do the same thing in the frequency domain. If you have a short period input, so if you have a source current that is changing very rapidly, then the measured potentials don't really get a chance to have very much IP effect. If you have a lower frequency, looks like this, then there's more time for the charges to build up. So you can use that as a metric. The one that's more used these days is phase. So you've got a current in a transmitter, it's going like this, and now you're measuring a voltage out here that is also going to look sinusoidal, but again, it's got a phase shift that's attached to it. And so you can measure that phase shift. It might be very small, just milliradians, a few milliradians, but you can measure it, and that's diagnostic. So any of those quantities are useful, and then the question is, okay, well, great, what do we do with that? The thing to do is to recognize that this IP, it's kind of changing the conductivity, but chargeability is just some number between 0 and 1, and usually it's pretty small, like 0.1, 0.15, something like that. So that means that the effect of chargeability is to put a perturbation on the electrical conductivity. So you can use that as like, okay, every time somebody says, oh, I'm going to perturb something, you say, Taylor expansion, right? So now you go ahead and you can write in perturbation mode that the IP data is just some charge ability with some sensitivity function pre-multiplying it. And this sensitivity function, this is important, is that this is the sensitivity that was used to get the DC resistivity inversion. In other words, what the IP is doing is perturbing that conductivity a bit, and the value of that conductivity is obtained through doing a full DC resistivity inversion. The bottom line is that we can write any of the IP data in this form of J times eta, where J is the sensitivity. So just to sum up, okay, IP data in the time domain can be anything that's kind of connected with this. In the frequency domain, it's usually phase, but it doesn't matter. This quantity here now takes on the same units as whatever this is. So if this was in milliseconds, that's in milliseconds. If this was in milliradians, that's in milliradians. If this was in millivolts per volt, the same, right? So we've got a linear problem, and that's nice. It's like gravity, right? It doesn't get much simpler than that. Just have a linear relationship. So we can go ahead and solve the inverse problem for that. So here's, we're collecting these IP data in exactly the same way that we were collecting DC resistivity data, right? So we can go ahead and plot them up in the same way. So we can use pseudosections. So here's an example. So this is a chargeable block. It kind of looks like what we had before, but now the background here is a uniform conductivity. But this is chargeable, and this is not. We go ahead and we do the IP experiment over top with the full level, and we get something. Again, the pseudosection would indicate that maybe there's something there. That's your chargeabilities and those things. Same thing as we had before. We throw on some. Now we throw little graphites or clays or something that's chargeable up top, completely musses up the data, or our GIF model where we have two chargeable, remember these are chargeable blocks, not necessarily conductive anomalies, that give you something like that. So again, you got to invert the data, but now inverting IP data is a two-step process. Because remember, I said the chargeability was perturbation connectivity. So here's how we do it. We go out, we collect the DC IP data together. And now we take what we ordinarily do and invert the potentials to get our conductivity model. Okay, so that's standard. That's our DC problem. The next step is that we're going to use that result to calculate the sensitivities. So once we've got that, now we've got the forward operator for our IP data, and we can invert that for chargeability. So that's the procedure. And this is a really old slide, at least these images. Is there anybody here that would even know of the Century deposit? Ah, okay, so this was stuff that was done about 1993. It was one of the first successful examples for 2D DC resistivity conversion. There was a guy by the name of Bob Smith who was around at that time in charge. And the Century deposit was kind of interesting because it was really characterized by the IP response and not by the conductivity. So here was the inversion for conductivity, got out something like that. So these are the horizons here for the mineralization zone. And so you first invert the data, you get this as conductivity. And then you get that to generate the sensitivity, then you invert the IP data, and you end up with something like that. So that was actually a marvelous success, and people were completely ecstatic about that. So for our baric prism, we end up with something that looks like that. So these are all completely analogous to what we saw this morning for the DC resistivity. So here we've got with the muck, we get the chargeable block as well as some of these other chargeables. And for this body, here, this example here, we've got two chargeable blocks. We recover them. Certainly enough to spot some drill holes. So what I'd like to do now, if there's any questions? Okay, I'd like to kind of go back to the case history that we talked about. So let's go back to Mount Isa. So here was that geologic model. We're going to change the data a little. We're going to change the question a bit. So in the initial setup, we said, oh, can we find something of moderate conductivity? Now we're going to say, can we find something that is both conductive and chargeable? Okay, that's kind of buried in these siltstones. Okay. So if we look at these various rock units, the two things that were particularly interesting, so there was this breakaway shale, that black shale, it was a very high conductivity. But actually when it comes to chargeability, it doesn't really have a lot of chargeability. Whereas that Mount Nova horizon, which was kind of, it has high conductivity, but not as high as the shale, actually has a high chargeability. And that differentiates it with these volcanics or various siltstones in there. So this is the thing, we always need to find, we always need to be looking for something which is distinct from its host material or its other units. So to recap from the DC resistivity, we had inverted the DC resistivity, got this great big conductor here, and sort of a minor conductor out there. For the IP data, here's an example of pseudosections. So it's the same, this pole, dipole, dipole, pole. Here's the pseudosection. So there's something chargeable, especially up at this end. But that does not give you a geologic model. So we're going to take these data and now invert them. So the way we do that is we first invert the DC data. We got that conductivity model, right? Now we take that conductivity model, we generate sensitivities, and now we've got the mapping for the IP data. Now we're going to invert those data with these as input observations. And here's the block unit. So now we're looking at a cube, again about 500,000 cells, and red is going to indicate chargeable material. So now you can see that something really interesting is happening here, right? There's a lot of chargeability kind of sitting up over here. That wasn't there before. So it's the same thing, we're going to turn around, we're changing the isosurface. Gradually looking at higher values. Kind of end up with that. So what we see, I mean, this is a complicated geologic area, unquestionably. There's lots of stuff that's going on here. But the big unit that we're kind of interested in is this guy here. That's going to connect up with the higher conductivity. So this is that Mount Nova horizon. There is some stuff in here. When we look at the conductivity, you'll see that this is actually inboard a bit from that. So it's not the black shale. And we kind of put everything together, and we've got these two sets of images. So from the resistivity model, we've got this. Okay. From the chargeability, we've got some chargeable stuff in here, but frankly, I don't really know what the explanation for that is. The really interesting line was this coming out here. That's the Mount Nova horizon. That's the one that's mineralized. That's the one that it's been productive. So I think this is a great result, right? You find it also kind of illustrates the importance of having multi-physical properties that are kind of impacting on the same problem. And if we have time for tomorrow, and if people are interested, it'd be really interesting to show you what we've been able to do for generating a geologic rock model just with airborne geophysics using gravity, magnetics, and EM, with the EM giving rise to both conductivity and chargeability. And gradually being able to put all of those things together and getting a geologic model that, yeah, it's great. So if there's time, if people are interested, you have to do that. Basically, that's it. The guy that was really of interest is this zone F, and yeah, corresponds to what they had found from some drilling, and was, yeah, very important. You guys have landfills? Worried about?
Quick question about the
Yeah.
IP there. So if the IP is a perturbation of the DC resistivity, would it make sense to use the IP model to go and back that out of the resistivity? Like, I mean, or is that to effect too small?
For most times, that's pretty small. Because a chargeability of 0.1 or 0.15 is actually pretty significant. But there are cases where, yeah, chargeabilities can be very high, in which case, yeah, it is actually important to kind of either do it all at once to try to find a complex conductivity that solves everything, or to somehow iterate back and forth. Yeah, so that, I think that's a problem that is, I would say, is still an active research area.
The time domain IP,
Yeah.
it was traditionally measured in the Iam time, but is there any reason why it's not routinely measured in the Iam time if it's not the same as
It's there and it is measured, but you can't separate it from the non-IP response. Because it's a perturbation, and so it kind of comes back to this question as to whether or not you should calculate the IP and then go ahead and remove that from the EM data and then redo the EM analysis. Generally what people do now, and this is again something I'd be really happy to talk about if people are interested, it's called EM decoupling. So if we, okay, here. So that's what happens. That's the ideal case. So there's no EM in that particular signature. In reality, however, there is. So that curve would go down and then kind of come back up, and so sometimes you'd have negative values in here, which is not that's just an EM effect, and it's affecting your IP signal that you've got there. So what people attempt to do is to try to find get an estimate of electrical conductivity and somehow remove the EM effect so that you're actually looking at that positive decay. So that is an area that is still very much of active research. We've actually done a lot of that stuff at the Geophysical Inversion Facility, and I think has come up with some really quite nice results. But, okay, well, I did see a big response for landfills, but there's actually some nice case histories. If people are looking for old landfills, generally they tend to look for conductive. The mental idea is that, oh, there's probably a lot of metal there, and so it should kind of be conductive, and I've got lots of ions, so I'm basically looking for a conductor. In fact, that's not a particularly good metric in a lot of places, because sometimes there's a lot of other stuff that's buried there. I mean, everything from waste of wall boards and construction debris, or sometimes it's green, plant-based material. The case history that I have, and you actually have it in your notes, shows that for a lot of these cases, the IP response was actually a more robust indicator that there's something buried there than trying to eke it out from the conductivity. So I think that's pretty interesting, and there's some places that we've gone to, especially Taiwan, was really interested in in that particular phenomenon. So. All right. Pardon me? Oh yeah. No. Why don't you do the apps now? Okay. Thank you.
So I'll do a quick interlude and show everybody where you can find the apps and get up and running with them. So there is actually, there's a website that we've started called GeoSci.xyz. I'll shrink this so you can actually see the whole site here. So there's a few resources available. Your mic is So we've got the GPG, and this is really aimed at introductory level geophysics. We use this for an undergrad course taught at UBC, but a few people are picking it up elsewhere. So EM is the resource we've talked about today. That's where you can find a lot on electromagnetics. There'll be write-ups on quite a number of the case histories that you've seen. And then SimPeg is the software that has been used for quite a number of the examples. So if that's something that you're interested in diving into a little bit, check it out. And there's a few resources on how to get in touch with us, because it is still being actively developed. So there's some startup things and things like that that you'll want to get in touch with us on. But to get to the apps, so if we go to Iam GeoSci here, there's some instructions for actually getting going with the apps on this page. So we've got two different styles that we've set up. Sort of the scope of them is pretty distinct. So the first one, we have these EM apps, and that was what Doug was showing for the most part. These are really designed to be simulation tools and toys. So you actually, like, everything is hooked up to slide bars. It's meant to be very low overhead in terms of computation. So the computation is all done under the hood. The simulation notebooks, in this case, what we've done is we've exposed everything for the computation. So if you want to actually go in and see how to simulate Maxwell's equations over a sphere and reproduce that first example that Doug showed where we compared the 3-loop example with the sphere response, that is all set up in the simulation notebooks. So if we want to go, let's go pull up the apps. So we've got these deployed on Microsoft Azure. So this is a service that hooks up Jupyter notebooks and lets you deploy them on the web. So this is the way I would recommend running them. It's free. If you want to actually go in and install this on your own machine, you can, and there's some instructions on the page on how to do that. Maybe. All right, so this is taking you to Microsoft Azure Notebooks. And so this page here, we're first just kind of looking at, we've got all of the notebooks listed. So there's 3 pages of them. There's 26 in total right now. And so what you'll need to do is, you can see Doug is signed in right now. If you weren't signed in, you could create an account, and it's all free. So here we're just going to clone this. And so this grabs updates or anything like that. You'll get the most recent version. So we'll overwrite because Doug has his own, or he's already cloned it. So we'll make sure that it's all up to date. And then we can go ahead and run these. So the one that we were looking at early on with the DC is the DC, the layer with the cylinder. And so what's actually happening when they're launching this is they've actually, basically, we've spun up a computer somewhere that Microsoft is giving us graciously, and then we're going to install the packages that we need that have been developed to run these apps. So that's all that's happening here. And so these are built, a lot of them with SimPeg, and then we've sort of built a little bit of a wrapper package that helps build all the visualizations and just make them. So if you download this at home, you don't actually, if you install these packages once, you don't need to go through this like install step every time. But because we're getting a new computer, so we'll do that. And then we can go ahead and walk through this notebook. So we'll import all the things that we need. And then here we've got this setup where we've got a cylinder in either a half space, or we can add a layer. And so this is now just setting up those plots for us. And so this is then something you can go ahead and play with. So that's the short version. Are there any questions on how to access these, or anything like that? Or resources? Or
how many concurrent users do we have to have access to? So, like, is that something that Paramount jumps on now?
It should be okay. We haven't run into issues with it yet, so it seems to be reasonably scalable. Yeah. Cool.
So what I think would be really useful is that, people could, take a look for tomorrow. So take a look tonight and just try download one, and just sort of see if the whole process works and just kind of play around a little bit, and it'll just kind of get you more connected with it, and then you'll be able to ask some questions tomorrow and just kind of get you in. I think that'd be really useful. So give that a shot if you need that. Okay. The future. Past, the present, future. Well, what I'd like to do is just sort of kind of try to sum up and kind of figure out where we were and where we might want to go. What did we cover? Well, we're not sure that we covered everything, but it's all in notes, and we can recover, do some more. We did DC resistivity, talked about EM fundamentals. We did an inductive source time domain. We did an inductive source frequency domain, time domain. We didn't do the HeliSAM, but we could. And we didn't do Magdalena, which is both the borehole and the ground. Those are both there. And again, people are interested in that. That'd be great. We didn't also do UXO. UXO is interesting because it's time domain EM, but instead of inverting things in a voxel model like we have, where you usually have 500,000 cells, here you're actually looking for parameters. So you model the object as decaying dipoles effectively in 3 different directions, and use that to kind of connect the object that you're looking for with the field data that you're working with. And the interesting thing there is it really kind of comes out like, okay, I've got to have lots of transmitters. So you build these instruments that have got multiple transmitters, so they're all in a rate of just a couple of meters, and they've got many transmitters in different directions, and you've got 3 component cubes that measure the magnetic field. And that actually gives you enough information that if you have an idea that there's a UXO in that region where you could obtain that by reconnaissance, you could go over this and then invert with this parametric model, and importantly make the distinction between, is that an object that I can leave in the ground, or do I need to dig it up? That's the big problem. Detection for UXO is fairly easy, but 95% or more of the objects that are detected should be left in the ground. They're not going to cause any harm. So discrimination is the real essential issue. And the case history talks a little bit about that. Methane hydrates, we didn't do. We did long offset TEM for basic salts, and natural sources for MT, GPR, but did IP for mineralization. So it's we missed a few things, but we've covered virtually all of the fundamental pieces except for the GPR. So with that, what's control? Well, here we go back to where we started with, we've got problems, high quality data, conversion capabilities, and web tools to communicate. So I said what we're trying to do is to get people connected and to promote the use and the usefulness of EM for a variety of problems. One of the big problems is monitoring, of course. Aquifers, you've got one right here, aquifer problems, as well as irrigation types of problems. So trying to figure out what's happening as a function of time, and what sensors you're going to put out. In the east, coal seam gas, I think, is important, but in general, Carbon sequestration is an issue that people are talking about, and hydraulic fracking. You're talking about. I was asking about geothermal energy. You say, well, it's basically hot rock, right? So presumably you're gonna put something in, frack it.
Engineered geosystems.
Yeah. So you gotta frack it, and then you're gonna want to know, okay, where's the fracturing going? What happens as a function of time? Do things get clogged up? All of those. Iam geophysics has got a potential role to play. Yeah, one of the problems that is, it's kind of taken the SEG by a bit of a storm, has to do with hydrocarbons and trying to use infrastructure that exists to see if you can excite objects and hydrocarbons at depth. The idea of this is that if we're sitting at the surface of the Earth, we've got a transmitter here, then we lose that geometric decay for the signal get down here. So here's a case where it kind of shows the essential problem. This cube might be like kilometers on a side. There's a region in here. Maybe that's going to be a CO2 sequestration, or maybe it's a hydrocarbon in a unit. And you want to pump stuff down, and you want to monitor it. If your transmitter is too far away from here, you lose too much energy to get down there. So if you could find some way of putting energy into the ground by putting a probe way down, that might be very helpful. So here's one of the things that's being used is take advantage of the steel-cased pipings that exist. So you could hook up a transmitter to that, basically funnel current into the ground and ignite the body up here, get some currents in there, and then measure either at the surface or in another drill. These kinds of problems have a lot of different application, and they have a lot of challenges from the point of view of how to work with them. First of all, there's changes in conductivity contrast. So the casing might be 10⁶ Siemens per meter, and permeability might be 50 or 100. The background structure here could be 1,000 ohm meters or 100 ohm meters. So you've got 6 orders or 7 orders of magnitude difference. You've got scale changes in physical size. If you look at a steel casing, you've got a centimeter rim on the side. That's the whole thing is maybe 10 centimeters in diameter. Right? So you got stuff that's 10 centimeters in diameter. This is going down kilometers, and you're wanting to look at stuff that's kilometers on the side. So it's huge issues in physical property values and in scale, physical scale. So that makes things very, very different. So just trying to figure out how do you work with those things? How do you model that and try to find out where the currents are going, and then maybe there's pipes that are corroded or something, and you want to find those. So there's lots of kind of issues with respect to actually carrying out monitoring processes. So again, here's an example. It's a pipe that's going down, and currents are going out. You have to model what's actually leaving on the sides of the pipe, and that's going to depend upon that. And things could get complex, right? You're going into a field that has got a lot of infrastructure. It's got pipes all over the place, casings, and then how do you know? How do you actually model this stuff? So here's an example. It's got a whole bunch of pipes that are coming down like this. You think, well, if I attach a generator to here, I'm going to put currents down through here. But if you actually happen to have a wire that was connecting one of these pipes to some kind of storage house, if you looked at what the potentials were on the surface, you'd find out, wait a minute, I'm kind of lighting up the storage house here. And it's just a like a single wire that's going there compared to what it should be. So I guess the point of this slide is that there's multiple scales, and when we come to tackle really serious applied problems, there's a lot of difficulties with respect to existing infrastructure and everything else that goes around. So, the numerical modeling that goes with that really requires, high-level performance computing as well as just advanced numerical techniques to happen. Choosing the right survey. I think this is something that crops up in many cases. People say, "Well, I want to find this, or I want to discover this, and will EM work?" Well, it's kind of a hard question to answer unless you start to be a little bit more specific on exactly what it is you want to know, and that question about what you want to know might change at different stages of the exploration project or different stages of the monitoring project. So here's an example. It has to do with SAGD, but really it's any kind of injection of steam someplace or anything like that. And the idea is that in these experiments, we've got a bitumen layer that's in a layer inside the Earth, and you drill a horizontal well through there, and you inject steam through this well. The steam kind of rises up and kind of melts or reduces the viscosity of the bitumen, which then comes down and then is collected by an oil-producing wellbore. Right? So that's sort of the overall idea, but what you want to do is to see, okay, can I actually image where that steam is? Can I image the steam chamber? And if you're going to try to set that up, you might also want to first of all decide, okay, do I have a right location for doing this? So that means you might need to do some airborne reconnaissance, then you might want to do some surface and borehole stuff, and then maybe some monitoring. So there's a number of different kinds of questions that come up, and each of them might involve a different EM survey. For the example that we have here, people connected with the hydrocarbon industry were really interested in this. This is a cross-section of the geology, and so the red here is a resistive region, and that's kind of a clay cap. Underneath here, there's what's called a McMurray formation, and it's really where the hydrocarbons are. So that's where the heavy oil is. And one of the things that you want to do is to find out, okay, where is this guy? How deep is he? So this is elevation, and you want to find that over section. So this is an area in Alberta. So this is 10 kilometers by 8 kilometers. And all the little dark spots in here are drill holes. So they drilled those and got the depths to the top here. And here's the result of the elevation map that was taken from those boreholes that are interpolated on. So you get, this is the elevation scale, varies by about 50 meters, and you get something that looks like that. So you take the airborne EM, so this is a time domain EM survey, invert those, and you get conductivity structures, and it looks like this. So this is a conductivity structure across this line. This is one across that. This is one across that. And from the conductivity structure, you can estimate what these, where the bottom of that is. And when you do that, you get this image here, which is actually really informative and remarkably similar to what was obtained with a lot of boreholes and interpolated. So that's kind of the reconnaissance, and that might play a role in helping decide, okay, where might I best want to do something to either inject steam or to do whatever. So then, if we now have like a pre-injection site, and you're going to want to try to know what your background conductivity is, because ultimately you're going to put stuff in and you want to see if you can have some changes. So the first thing is to have a pretty good idea of what the background conductivity is. So that might involve doing some airborne EM work, as well as maybe some ground work with perhaps some large loops, and then using that to get a better conductivity structure, and maybe even put a borehole down and perhaps have a surface loop and having some measured fields down here. You take all of those, so that's different surveys, and a different 3D inversion to get out that conductivity. And then the next step, and this is synthetic, but actually it turned out to be really quite nice. So now we've got horizontal wells that are going in the ground, and you're injecting steam into them. And those steam, so you're injecting steam from the bottom, and that steam kind of rises up to the top, and there's three wells. So 3 horizontal wells going in. And then to see if you could then subsequently image these. And what made this one more interesting, there was a little restricted zone in here that, so there wasn't as much steam there. So with the surface transmitters and just the borehole receivers that are in wells that are mandated because they're observation wells, inverted the vertical electric field component and ended up with an image like that, which not only showed you the wells, but also this zone that had been kind of blanked out. So I think that shows that a couple of things. One is that EM can, is kind of nicely tuned to some of these problems that have conductivity contrast near surface, and secondly that you've got some degree of resolution in actually maybe finding kind of void zones. Marine EM, I've mentioned this a couple of times. There's a lot of problems connected with marine. There's gas hydrates. They're worldwide. I think in Australia, your gas hydrates or methane hydrates are sitting right around this edge here as far as being the highly potential values. Marine massive sulfides, submarine massive sulfides, the Japanese are very big on this, and there's a couple of other countries too. So you get these black smokers that come up, and you've got minerals that are simply deposited on the surface. So maybe in the top 10, 20, 30 meters, you've actually got a high concentration of minerals, and the potential for going down, having machines on the ground, digging this stuff up, funneling it back up to a boat. That technology exists, and it's quite doable. So what is required is to do marine experiments to try to find out where those particular conductive bodies are. And then also marine EM for sort of tectonic types of problems. So this is both controlled source and MT that could be put on the ocean bottoms and then inverted to recover the electrical conductivity structure. And also in this case, the anisotropy. We didn't talk about that, but conductivity doesn't necessarily need to be homogeneous in a small region. It could actually vary in direction. The fabric of the rocks could conduct electricity much easier in, let's say, one direction than the other. And this is the case of that. This is the ratio of the resistivity in the x direction versus the y, and there's a substantial difference here in this region between those two. So it's more resistive in one direction. Then you've got large scales. You've got OSLAM. Who here is connected with OSLAM? Good. You'll have to tell us more about it tomorrow. And the similar thing in the States with EarthScope. There's a little hole there right now that they're trying to fill up. Water, a big issue everywhere we go. So aquifer monitoring, management, saltwater intrusions. That's something that's important in Australia as well as elsewhere. And pollutants. So monitoring, trying to find out what you've got, trying to figure out how best to use the resource. Aquifer storage and recovery, where you pump water down and try to recover it. But when you're pumping it down, you want to try to figure out where it is. So there's lots of potential there. Data integration, multi-physics. This is, EM does something, but it's really a combination of EM with seismic, with gravity, so that, or magnetic, so that you really integrate all of these different properties. We've got a very nice case history that's connected with kimberlite pipes and using airborne geophysics to jointly invert all of these, to invert all of these data in 3D and to come up with a 3D geologic rock model. So this was gravity, magnetics, frequency dominium, time dominium. And in doing that, we also were able to get the chargeability, which this is a lot of work that was done by the other presenter that sometimes with me, Sagi Kang. I think this is the first time that we've actually got three-dimensional models of chargeability from airborne data. So the result is actually really nice and able to take the 3D inversion results of these, generate geophysical rock models, like rock 1, 2, 3, we don't know what they are, but with some additional information from geology, and especially if you happen to have a drill hole, you could identify what these things are. And if that had all been done in retrospect, they could have saved themselves a lot of anguish and money. And here is now we're really kind of opening up where we want to go. We've got the future with modeling and inversion. We've got all the pieces. We've got high performance computing, cloud computing, collaborative development, and all with kind of an open source concept. And we'll talk tomorrow. Lindsay will give you a lot more background about SimBay, how to use it, where it's been used, and all of the examples that have been run today, all the Python notebooks, they've all been developed with the SimBay modules. And this interactive computing and inversion, I personally have been really quite struck by how insightful this is. The fact that you're able to convert equations not only to a picture, but also to a picture that you can interact with is huge. And suddenly you can find yourself learning something that once you learn it, it's like, well, that was really simple. But before you do that, you can't get there. And a large part of this is actually being able to solve your problem in 3 dimensions, so that, because your fields are 3-dimensional. And if you can visualize the 3-dimensionality of the fields, then it's really easy, to make a projection and say, oh, well, I've got an X component I'm going to measure here, and now you can kind of see what it is. And then you can make a traverse of this, right? So you can get, oh, here's the EX component along this particular line. That's right. When I was learning a lot of this material, and if you look back at the old books, the way things were taught was that they would sketch out a problem, a physical problem, and they would show, okay, well, here's the EX component if I went over here, right? And like, okay. And they had books of type curves of this and that. And honestly, you can look at a zillion profiles and you don't get any clue as to what things look like. You cannot go from a low dimension to a high. However, if you start with a high dimension, you can easily project onto a lower. And that's what makes all the difference in the world. And so having kind of interactive apps that you can and visualize the results, ask questions, and importantly, ask what-if questions. So that when you're using the apps, I'm hoping that you're not going to just do a slider bar and say, oh, that was interesting. The way to do it is to say, okay, I'm going to move the slider bar this way. That's going to make this thing more resistive. What's that going to do to the currents? What's that going to do? Am I going to get charges that are built up? What's going to happen? So force yourself to think about the outcomes. And just be there, be critical, write it down. And this is what I think is going to happen. And then you press the button on the go, and then you see what actually happened. And that's a very powerful way of learning, because if you agree, if the result agrees with what you had predicted, you are good to go. You probably really understand what's going on. If they disagree, then you have an opportunity to learn. So that's the way to use the apps. And collaboration. We mentioned this a number of times, but here is really, I think, where an important future development is. Everybody is, you cannot believe the number of people that I have seen that have done the same, 1D forward modeling code or 1D inversion, or asked the same kinds of questions and gone ahead and developed things from scratch. And it takes a long time, and they don't really, it's a very difficult process. However, by collaborating, by having open source resources, a graduate student can greatly shorten the amount of time that it takes him to get up to snuff, right? And so you build the computational expertise and the understanding of that problem much more quickly if you've got open source resources, you've got people to collaborate with. And then once you've got that foundation, then you can go ahead and start your own problem. So we have this opportunity to collaborate. We've got resources on Iam GeoSci. You can edit them on GitHub. You can ask questions. You can raise issues. You can contact people on Slack. I have a Slack channel that has people kind of all around the world, and ask questions and collaborate. And with that, you can really advance your own personal knowledge as well as advance the field. So that was it. Our goals with this was hopefully inspire you and increase that use and usefulness of geophysics through application case histories. Build that foundation. Set realistic expectations. You're now going to know that if you're working with Iam, you're not going to get incredible resolution. It's not going to be like the same as Saturn. Everything is diffusive. That's okay. Get something. And try to promote a community for development of open source software and capturing case histories. So the resources, there's GeoSci.xyz. We've talked about Iam GeoSci, but there's GPG, Lindsay mentioned this, there's SimPay, there's our disk, there's case histories. So this is a portal to all kinds of things that might be useful. And of course, there's the apps. So I'm not sure if you can appreciate, but there has been an incredible amount of work that has gone into developing all of this material. And it's really the result of the disk team, in addition to Lindsay and Saudi, are kind of co-presenters with me. There's just all the UBC GIF team at home, and now more and more people from other countries that are kind of contributing. So it's really great to see all of that develop and to see things come together. So tomorrow, I'd like everybody, I hope people can come to Disk Lab Day. It's kind of open-ended, as I've said before. It can be tailored to a lot of things. If there's still some things that you feel we didn't cover in here with case histories or material, we can do that. We'd very much like to hear from you as to what problems you're working on. This has been tremendously successful. We don't want it to be a burden on you, but what I request is that maybe each of you could put together, I don't know, 4 or 5 slides, no more, and just plan to give a very short talk, a little lightning talk, maybe 5 minutes. Just to, okay, so we've kind of got an idea. These are the problems this is the problem you're working on. This is what you're facing. Or this is what you want to do. Anything, right? Just get us connected. And we'd like to actually capture those if you're willing, so that we could deploy them on the web. And then people would know, like, okay, well, in Perth, people are working on these kinds of problems, and isn't that interesting, or whatever. So I really hope that people can participate in that. First of all, how many people are planning to come tomorrow? So only about half. Okay. For those people who come, would you be willing to just give a short talk? Very informal. Yeah, well, how many would raise your hand? You can raise your hand up so I can see it. 1, 2, see it? Is somebody else working on a problem? I mean, it's not a big deal, right? But you've been listening to me for 8 hours, right? Just listening to you for 5 minutes. Well, surprises, right? Like just a couple of slides, or even if you don't want to have to put together slides, be prepared to stand up and say, look, this is what I'm working on. And it should be, at least try to have some connection with Iam. Right? So that, here's my problem. Do you think Iam could work? Actually, we had some really nice discussions with people in geotechnical engineering. When we were in Colorado, they were building tunnels, and trying to figure out, okay, could Iam be of use in this kind of situations? So, what kind of transmitter might I use? Just talk. So I hope that people can do that. And then with that, that's kind of a nice basis to have continued conversations. So in addition to that, we'd like to present, Lindsay will talk a bit about SIPEG, its structure, how it works. And we could also provide tutorials on both forward modeling and inversion if people are like, we're kind of easy, we've got a ton of stuff. And we just like to make sure that during the course of the day we're effective. So that's our only goal. So you can help us out on that. And yeah, with that, thanks. So I have only one request, and that is there is a feedback form. I really would like you to fill that out and hand that in before you go.